Stace. Oké, oké. Dat is mooi. Ja, kom naar binnen. Is goed, hè? Ja, zo heb ik het gisteren eigenlijk ook al gedaan. Ik dacht, ik vond daar ook wel mooie uitslaan het groen. Dat level. Wel? Ja, kan wel wat harder. Nee, ja, die kan wat. Ja, precies. Ik kan hem wel wat harder zetten. Kan hem wel wat harder zetten. Dus, ja. Bij. Doe een beetje zo. Of gewoon hier. Oké. Ja. Ha. Fantastisch. Fantastisch. Oké. Goed. Ja. Ben je tevreden?
Welcome everybody. My name is Rona. I'm a moderator for this session. Let's please welcome to our first speaker, Mr. Lauren. Thank you.
Thank you. So let me introduce you to the organization Julia GNSS and some of the packages that I implemented. So back in the days when I worked for a university, we tried to build a robust GNSS receiver. You know, the satellites are quite far away, and the signals that arrive at the Earth are low powered. So it's very easy to interfere with them. So we used antenna arrays, and with antenna arrays you can do fancy stuff. You can, for example, amplify signals from certain direction of arrivals and mitigate other signals from other direction of arrivals. So here, for example, we have a jamming signal that's mitigated coming from this direction of arrival, and we have the signal of interest, which is, for example, a GNSS, a GPS satellite that is amplified. But you can also do other fancy stuff. For example, you can estimate the attitude of an antenna array in terms of yaw, pitch, and rod angle. And this is me here rotating an antenna array with four patches, a 2x2 antenna array. And you can see me rotating the antenna array. And on the right side, you see the attitude estimate of this antenna. And you can see they match quite well. It's just by using the GNSS signals without any inertial measurement unit or so. So back in the days when I started, we always recorded the measurements to file because our receiver that we've implemented at that time wasn't capable of doing anything in real time. We used software that starts with M. And then I found Julia, and I sat down and I thought about how to make this work in real time. So when looking at it, you can essentially split apart the receiver in 2 or 3 components. So there's the down conversion and correlation. This has a high data rate input, so you can think of the signal that comes in with a bandwidth of a minimum of 2 up until 20 megahertz or even 50 megahertz. And then after correlation, the signal is compressed, and after that you only have a signal of the data rate of 1,000 hertz or 100 hertz, depending how long you correlate. And then you can do the code and carrier, Doppler estimation, frame synchronization, decoding, and in the end, the user position. All of those are low powered. These functions don't need to be that fast. So I sat down and wondered how can I make the down conversion and correlation really fast so that we can do that in real time. So, and I'd like to walk you through the journey of generating sine and cos values to down convert the signal. So this is only part of what needs to be fast. And the first function that came to my mind was the KISS function. It generates the cosine and the sine values in a complex fashion. And you can see here, I calculated with the Doppler and the sampling frequency, and I benchmarked it with 2,000 samples, and that correlates to data of 1 millisecond. And you can see that the benchmark for this KISS function for this 1 millisecond of data is around 20 microseconds. So you can think of it, you can process 50 satellites in parallel with this function. But remember, that's only the sine and cos value calculation, but you still need to do the down conversion and the correlation. So that was nowhere feasible to do in real time. Then I thought about maybe we can get better if we use the float 32 instead of float 64 to better use the SIMD efficiency. Yeah, and it turns out you can do a little bit better, but still it's not feasible for real time. Then I implemented my own sine and cos approximation using polynomials, and I thought about we already have seen this reduction from 64 bits to 32 bits. Maybe we can do better with 16 bits. There's no float 16 bits, so I implemented everything in integer 16. And it turns out you can do much better if you use this float 16, the int16 integer values. But that comes with the problem. We also need the phases in integer 16. So to calculate the phases, it takes roughly 1.5 microseconds, and in addition with the sine and cos calculation, you are around at 1.7 microseconds, which is okay. You can do that in real time then, but at the same time, loop vectorization came out, and this was capable of doing it just in 1 microsecond. So I used that. So I did this benchmarking with all the things that need to be fast, like down conversion, sine and cos calculation, and correlation. And I'm happy to announce that it is now capable to do this in real time. So here I had a software-defined radio platform hooked into my computer, and you can see here on the left side, it tracks the satellites in real time, and I will show you in the next picture. Here on the left side, it shows the signal-to-noise ratio, or the carrier-to-noise density ratio of several satellites. Here in the middle, you see that the direction of arrival of the satellites, and here on the right side, you can see the position of the user in latitude, longitude, altitude. Yep, that's it. Yep.
Many thanks for the interesting talk. I have a question related to, I'm quite new to Julia. How was the interfacing to the software-defined radio that you used? Were there already packages available?
Yeah, there is one package available that uses the SOAP SDR, which is SDR software platform that you can use with several different hardware platforms, and I used that.
Okay, thanks. Thank you.
Yeah.
What sampling rates did you use?
So in this case, it's just 2 megahertz, because the software-defined radio platform, the RTL SDR, isn't capable of doing more. But the software that I implemented is capable of going up to 5 megahertz or even 10 megahertz. I haven't tested that really. What was crucial for me was also to not only process one antenna signal, but multiple antenna signals. And yes, you can all of that. You can do that all in real time.
If you do multiple antennas with RTL SDR, how do you phase lock them? Because they all have their own oscillators, right?
Good question. I haven't used the RTL SDR for that. I used an Ethos software-defined radio platform for that. They have this phased array thing, but I know that there's a project called Kraken SDR, I think, which combines the RTL SDRs together. I think there are five of them combined together with phase locked, but I haven't used that thing yet.
So you said you started with MATLAB,
Yeah.
and then initially, and
Yes.
then you couldn't get to the speed, and then
Yeah.
you started in Julia, and you added a lot of optimizations.
Yes.
Would it be fair to also check how some of those optimizations, what it would yield in performance in MATLAB?
Yeah, I think you could, if you put really hard work into this, you could also make it work in MATLAB, work in real time, because in the end it's a lot of matrix multiplication. This thing that needs to be really fast. Yeah, I'm not totally sure. I haven't tested. So
Okay, thank you.
Can I start? Okay. Hello. This next talk is a Julia case study in the pharmaceutical industry. In particular, we are building a Bayesian nonlinear mixed effects model to improve powder storage. So powders are used all over the pharmaceutical industry to make tablets and pills. And they are typically stored in silos. So to visualize a silo, you just think like these large grain silos that you might be familiar with from agriculture. It's basically the same thing. And then models are useful to judge the safety of these silos, that the silo does not tip over or collapse, for example. And for powders, this is typically done using the Janssen equation. And this Janssen equation contains unknown parameters which must be estimated from experimental data, and particularly the K, the A, and the B values we are interested in calibrating. To this end, we have a first measurement set up here, where we again have powder in a silo, in a column, but the new thing is here that a force is applied at the top of the silo, which causes the powder to compress, and then what we end up measuring is the height of the powder at equilibrium and also the force at the bottom. We can build a model for this by considering an infinitesimally small layer of the powder and look at the force balance of that layer. There are all kinds of forces acting here. For example, a gravity force and also a friction force. Using this force balance, you can come up with a differential equation, and if you solve this differential equation, you end up with this equation here for the force or the stress at the bottom of the silo. This equation is very similar to the one I showed on the previous slide, except that here it takes into account this force that is applied at the top of the column, and then we gather measurements for a variety of different forces applied at the top, and then again the goal is to estimate this K, A, and B parameter, except there is an issue here in this equation in that the K and the A parameter always occur together in the equation, and this means that the model is unidentifiable. There is an infinite there are infinite combinations of K and A which all fit the data equally well. And to remedy this situation, we had to come up with a second measurement setup. What we see here is that we now apply a force to the powder, and then what we measure is the friction force on the wall of the silo. And as you push harder on the powder, of course, the amount of friction also goes up. And this is modeled well with just a simple linear regression model. We repeated this sequence of measurements where we push harder and harder on the power 3 different times, and then we noticed that measurements coming from the same repetition are more similar to one another than measurements coming from different repetitions. What do I mean by that exactly? Well, for example, in the first repetition, those are the dots in blue. Those dots are always at the bottom of each of these 3 points. Then for the second repetition, the measurement in orange, those are always at the top of each of these 3 measurements. So there is definitely some additional structure present in the data, which means that it is likely a good idea to introduce a random effect into the model. This means that this slope A here is no longer just a single value, but now we say that for each repetition of the experiment, A is drawn from a possible distribution of slopes, typically a normal distribution with a mean and a standard deviation, and then the goal shifts towards estimating this mean and this standard deviation. So about the previous slide, I said that the model was not identifiable because the k and the a always occur together. Here in this equation, we see that the a is present alone, so it does not have this identifiability issue, at least regarding the a, but the k is not present at all in this equation here, so we can't estimate k from this setup. So we see that only considering the first measurement second or considering only the second measurement setup will never allow us to estimate all three parameters of interest, the k, the a, and the b. So we somehow need to come up with a way of joining these two data sets together, and this is why we used Bayesian statistics. And for Bayesian inference, you always need two ingredients. The first ingredient is prior information. We had bounds available for all of the parameters of interest, so that can serve as a prior. And then the second ingredient is the likelihood. And in particular here, it is not that difficult to calculate the joint likelihood of both measurement setups together. This is in contrast to if you took a more traditional statistical approach using frequentist statistics, coming up with a way to quantify uncertainty there for both of the measurement setups together would be quite difficult to achieve, but with Bayesian methods, it goes kind of automatically. And then the most important part of this talk, at least for this conference, is why did we choose Julia to implement this? Well, the main reason is the excellent Turing package for Bayesian inference, which works well out of the box with differential equations. I mentioned previously that, that these force balances are related to differential equations. Now, in this case, it turned out that the equations were simple enough to solve by hand, so that we did not end up needing differential equations. But at the start of the project, we did not know that, and there are also extensions to these models which lead to differential equations not solvable by hand. Then another important consideration was that the scientists and the engineers doing hands-on work with these silos, they are familiar with MATLAB, and the Turing syntax is quite similar to what they are familiar with in MATLAB, at least more familiar than, for example, using another Bayesian inference package like Stan. Indeed, this Turing code is very concise and very legible. So on the left-hand side, you see the full mathematical description of the model that we ended up using. And on the right-hand side, you see the Turing code implementation. And you see that it is almost a line-by-line comparison. For example, here, the first line, this prior distribution for mk, this equation here is almost exactly the same. Very similar for this likelihood equation for tau. The equation you see here is almost exactly the same. For this reason, we were able to quickly iterate on this model, which then led to good end results. I don't have the time to do a deep analysis here of the results, but just to summarize things, we ended up with nice posterior distributions for all three of the parameters of interest, the k, the a, and the b. Thank you for your attention.
Sharing your knowledge. Let's move on to our next presentation with three people. Yes, we have three speakers.
Oh, that's actually just one, but that's
yes,
good.
here you are.
All right. Hi, everybody. My name is Curtis Vogt, and I work with Beacon Biosignals. Today, I'm going to talk about the prototype Julia project, Ray.jl. So Beacon has been using distributed computing for some time now, and mainly we use distributed.jl for this purpose. And we've run into kind of a few challenges as we've done this, but we've also developed some in-house tooling as we've kind of gone along. Yeah, some of the user stories we've identified we wanted to kind of solve was we wanted to be able to deal with ingesting large amounts of semi-structured data, dealing with exploratory workloads on large time series data, and also workflow orchestration for our inference pipelines. A couple different tools we ended up looking into as part of this work is we looked into Apache Beam, Spark, also Argo workflows, transducers.jl, and actors.jl. Ultimately, we decided to do, we tinkered with all of these tools, but we ended up doing deeper dives into both Ray for Python and with Dagger.jl. As part of this work, we also realized that using toy data sets, or sorry, using toy kind of problems to put into the distributed frameworks only got you so far, and we needed kind of like a realistic benchmark in order to get realistic results. So what we ended up choosing for that realistic benchmark was using EEG spectral features. That's a realistic workload for Beacon Biosignals. And it was also simple enough that we could port it to different programming languages without it being too much of a hassle. Sorry for the blinking there. Eventually, we ended up continuing using Ray and not Dagger.jl. I'll get onto the reasons for this in just a little bit. And kind of one of the milestones we accomplished with this work early on is in order to see if we wanted to use either continue with Ray in Python or Ray in Julia, was us using Julia and calling the C++ shared library that Ray provides in order to store data in their object store and then retrieve that data back out. So with kind of some proof of concepts to prove that we could kind of work with Ray in Julia, we ended up working on this Ray.jl MVP focused on the real-world benchmark. So I need to answer now why we didn't go with Dagger in the end. And so basically, during our experimentation, we just ran into a lot of issues. And kind of a big concern for us was that it was hard to debug these problems. And we have a lot of kind of users in-house that are less experienced with Julia, and we didn't want kind of the pain points of trying to teach them all of the nuances of having to deal with Dagger.jl. Also, Dagger uses distributed.jl, and that turned out to be a lot of where our problems were kind of coming from. Ultimately, what we wanted is something where you could submit a workload and then have the cluster automatically scale up to fulfill that workload. Also, Ray just had some interesting features that we really wanted to kind of look into. One was the shared memory system it had. It's object store, and some features I'll talk about in a second there. And it had that automatic resource scaling we were talking about. So that was something we really wanted to look into. And finally, the ultimate reason was that it was just kind of more battle tested. So the whole idea of this Ray.jl MVP would be we would have to write kind of the front end for Julia, but the back end would end up being entirely what existed. And so we didn't have to write that stuff ourselves, and we could get kind of the reliability for free there. So I need to talk about some key concepts in Ray kind of before I proceed here. Basically, a Ray task is just a regular Python function, a non-class function that you execute kind of remotely on a Ray worker. There are actors. This is basically, you can think of as a stateful function. Specifically in Python, how this works is you take an instance of a class. That instance gets assigned to a specific Ray worker, and then any method you call on that instance are then run against that one specific worker. And then so you get a stateful-based implementation. We didn't end up implementing that in Ray.jl. That's mainly because the MVP didn't require it. But we did identify that multiple dispatch was a unique challenge to get this implemented. Additionally, there's objects. They're immutable, and they get stored in Ray's distributed shared memory. And you can also specify resource requirements for both tasks and actors. So you can say how many CPUs that this kind of function requires, how many GPUs, and there's memory restrictions. And that's useful for the Ray scheduler in order to both assign your workload to a node that can fulfill those requirements. And also it's good for the auto scheduler for being able to bring up the right amount of resources. So I need to talk about array objects. Once again, they're immutable. That is important properties for the object store and how it kind of manages them. And also it has the capability to do zero copy reads. So in Python, if you're specifically working with a NumPy array, what you can end up doing is storing like a multi-gigabyte array in the object store, and then you can have multiple array worker processes in Python read and index into that data with only having the one copy in memory and not having to copy that data into the individual worker process memory. The object store, also some properties you need to know, include it's distributed in that every array node has a copy of the object store, and then it uses reference counting for dealing with garbage collection. That's an important detail for the client side, because if you don't implement that properly, your objects could disappear on you. And also it had some nice fault tolerance capabilities. So if your node would suddenly, your array node would suddenly get terminated, the associated object store is also terminated, and objects in there are lost. But it can end up recovering that data by looking at other object stores, or alternatively, if there isn't any copy stored, it can end up rerunning a task in order to reproduce the result and automatically recover. So on the client side, you don't end up working with array objects, you work with object references. And those are created in two different ways. One is with array.put, where if you want to store kind of your own user data in there, you can put whatever you want in there. And the more common way is when you create array task. So every time you make array task, the return result of that is an object reference. These are very similar to distributed.jail's future type, specifically in that they can reference data that has not yet been created. So when you make array task, you end up getting an object reference back, and that object reference may point to some unfulfilled data, and then only when you need to retrieve the content of that data does the call block, and then you end up having to wait. These references can also be passed between workers. So once again, if you submit a task, you can pass in that object reference as a parameter to that task. So I'm going to talk a little bit about installing array at the moment. Unfortunately, it's not as easy as just doing a package.add. And mainly that's because there's some complications around kind of our binary builder setup that we have to resolve yet. But the things you need to know is basically follow the instructions at the bottom of the slide here, and be sure you're using the dev instructions and not the stable ones, because I did a bunch of corrections recently. And then the other details are that specifically you need to use a version of Python between 3.7 and 3.11, and a version of Julia between 1.8 and 1.9. Those are just restrictions right now. We're trying to solve all that. We also haven't registered the package with General, and that's because we kind of want to sort out this mess before it's actually registered. So now for the examples. So here's an example in both Python and in Julia for storing data in the object store. So it's pretty simple. We end up taking your user data, put it in the object store with array put call, and then end up retrieving it with array get call. So you can see the interfaces between Python and Julia here are very similar. And ultimately, the Python design worked in Julia well, so we just copied that over. And then what you need to know on the Julia side is that we end up using Julia's serialization standard library for storing data in the standard, in the object store. So basically anything that's serializable will work here. As for tasks, here's an example in Python. And so basically the basic line by line here is we end up initializing this Python process as array worker. We then define a array task definition, that square function, and then we end up executing that array task with 4 different input values. And then we get back 4 different object references, and all these tasks end up running asynchronously, and then only when we call the array get call, we have to block and wait for the results here. The important details here is one is that array.remote decorator at the top of the square function. That ends up translating the Python function definition into the array task definition. The important part of this is basically you can't run square as a regular Python function here. So that's why we need that .remote syntax there, because it's disallowed to just call it a square. In Julia, that was actually something we wanted to get away from. We wanted to be able to call any arbitrary Julia function as array task. And so what we have here is we have this submit task function that we have, and this is intended to be a low-level interface for submitting array tasks. We haven't worked on a high-level interface for it, but basically this is mirroring the invoke syntax maybe used to. And then, yeah, it's the same thing again. We submit 4 different Ray tasks, end up getting the object references back, and then have to wait for the results. So here's a little bit more of a complicated version of this same thing, where we've updated the square function to now be able to dereference object references which are passed in. So the details here you need to know is we use Ray put in order to put some data into the object store. We then to have this list comprehension where we end up submitting 4 Ray tasks which take in object references back into the square function there. We need to dereference those objects in order to do the computation. They get returned, and then we get 4 more object references back, and then we get the values back and we can show it that way. But also, now because we can run square as a normal Julia function, we can do things like on the bottom, on the second last line, you can end up calling square as a normal Julia function, pass in those object references, have them be dereferenced, and then get the same values. And you can also pass in actual literal values and get the same results. And the way that works is the ray.get function works as the identity function if it's passed in a non-object reference. So back to the benchmark for a bit. So this is just a high-level overview of the EEG spectral features benchmark we ended up using. And so it's kind of 2 parts here. One is we ended up using a package we've open sourced called mocktablegenerators.jl, which ends up generating our input data we use for the algorithm. And that was a combination of arrow files that we generate and LPCM files. And the algorithm itself, what it does is it takes a time series data, splits it into segments or chunks, and then what we would do is we would compute some statistics on each of those chunks in parallel with Ray, and then we would take those statistics and calculate in parallel the features that we were interested in, and then ultimately end up reducing those into the final set of values. And so ultimately this is just a map reduce, but it was kind of a realistic workload and something we wanted to parallelize. So here's some of the results. So this is the total amount of time it took to run Ray and the original algorithm. The original algorithm there is in blue, and then the other colors are running on a single node Ray cluster with 4, 8, and 16 different workers. And we can see here there's some good speed up. This is the actual speed up graph. Same information again, just as a speed multiplier. We're actually getting a 12 times speed up for the 16 Ray worker cluster over the original results. And overall, this graph here is just basically saying or showing how much or that our benchmark is scaling quite well with the number of segments. Oh, something I neglected to share is that number of segments value at the bottom is basically we ended up running the algorithm over a different subset of segments, so we could run it on different resource-constrained environments, and then we could kind of extrapolate the results for how better things would be if we'd have even more segments. So this one here shows kind of the latency the ray.jl package was introducing over the original algorithm. So the original here is actually the fastest because it doesn't have that kind of latency. And in the worst case scenario here, there was 8 seconds of latency, which is really not great for Ray, but on average, it ended up being 2. So as we would add performance improvements to Ray and kind of like fix ray.jl, and as we would fix things, then we'd see these lines starting to converge. We also did some tests on multi-node clusters. So these graphs end up being a little busy, but the Ray local is a single node cluster. Ray cluster is the multi-node cluster, and the original is the original results. We also ended up doing some larger amounts of segments for a limited number of configurations. So we have 1,000 segments in this case for some. So here's the speed up graph again. Also, it's a little bit crazy here, and unfortunately some colors kind of are too close. But really the key takeaways from here is more vCPUs equals more speed. And basically, if you have the equivalent amount of vCPUs, then using fewer nodes is better. And ultimately, this makes sense because if you're dealing with multi-nodes, there's some cross-communication you kind of have to deal with. But even in the multi-node, we're seeing some really good speed up over the original. And then this graph shows the Ray latency again. And this one I think is actually particularly pretty interesting because even though with the multi-node cluster, we're seeing some serious extra latency being added, where you can see up to like 80 seconds of latency with the multi-node cluster. But as the workload increases, especially with 1,000 segments, we end up getting pretty close to the single node cluster performance and even the original performance. So basically, really what this shows is you shouldn't run the multi-node cluster if your workload sizes are way too small. It's not worth it. And you can see that, especially in the beginning, it's way worse. We also did an extra thing with the multi-node cluster. We kind of timed how long it took to spin things up. And so the time axis here is showing the time between when we submitted a Ray workload and then the total amount of time it took to get all the nodes online. And so the details here are when we used larger instances, it was a bit slower, but the difference between the smaller node instances and the larger node instances is about like, what's it, 4 seconds, 4 to 8 seconds. Not a huge difference, and ultimately it took 60 seconds. But something I should point out is this an absolute worst case scenario, because as your Ray nodes would come online, the scheduler would automatically start scheduling work and start doing things. So depending on your workload, it may be good to use smaller nodes because they come online faster, and you can at least get some of your work started. Some additional findings that weren't included in the graph is that just this automatic scaling stuff ended up working really nice for our workload. Allowed kind of users to not have to think quite as hard about how many nodes do I have to bring up ahead of time in order to get these things done. Something I thought in particular was really nice for cost savings was scaling down during execution was possible. So if you have a very bursty workload that needing a lot of nodes early on, but not so much later, because the Ray scheduler is aware of what nodes are actually being used and can scale down those nodes while the workload's still running. Additionally, the Ray resources are logical and not physical, so that can bite you if you end up saying your 16 vCPU node has 100 vCPUs. It'll overschedule in there and can cause things to crash. But it's also nice because you can give yourself a buffer and you can say my 16 vCPU node actually only has 12 CPUs on it, and that way you have a buffer if you didn't quite set your resource scheduling correctly. We also ran into some issues with memory during running these benchmarks. The problem there, we expected the Ray task would automatically retry when a node had failure. We thought we had some memory leaks going on, and that we should just have it automatically reschedule. That just turned out to be a bug in the Ray.jl code, and we've since fixed that problem. So we have automatic retries, and those kind of failures were less annoying. I have a little bit of time still. It's good, so I can get to some tangents. So something we ran into, and you may have noticed before, I was just using anonymous functions in the examples. And the reason for that is because when you're dealing with serializing named functions in Julia, they're done strictly by the name. So you don't actually get the contents of the function definition. And so this was problematic for like functions that were defined on the REPL. You couldn't actually serialize them and then send them over to the other workers. But those familiar with the distributed.jl may wonder, well, how does that work? Because it does that. And it turns out they don't use the base serializer. There's a custom cluster serializer that what it does is it tracks global references and automatically keeps things up to sync as they get changed. We also require a custom serializer, but for our needs, that's for dealing with the reference counting, because we need to know when object references are embedded inside of other object references, and so we need to kind of indicate that information. So we ended up doing some soul searching, and we're wondering if we really needed to support globals for this MVP. It turned out we didn't, for the most part. We didn't want closures, but we did want to deal with named functions in some form. So we kind of went about it in a different way. The problem with the whole closure setup is kind of this, is if you look at this example, which doesn't work in Ray.jl, try to consider what you expect would happen. So if you have like 4 Ray workers, would you expect that all the workers would have the global X initialized to 0 in all of them? And so the result of this call count for all these would be 1? Or maybe you would expect that X would be shared across the environment, and that meant the last executed task should always be 4. Now, the problem with doing that last one is it ends up being really expensive for sharing that information and keep it in sync. And it's something we weren't really interested in doing. I think probably the former of saying, hey, they all initialize to 0 would be more reasonable. But it's something we didn't need to tackle, so we just said, this is kind of crazy. We did want the named functions, though. So this is the solution we ended up going with. We have this Ray import macro, which is basically, we can say what packages we want to import before we initialize the Ray workers. So ultimately we just said, okay, we're not going to support named functions on the REPL for now, but we are going to support named functions within packages. So you can import and then use all your references that way. So it kind of forces you to use a better workflow than just entirely in the REPL. Although ultimately it'd be nice to have that for just experimental purposes. And then I have a little time to talk about this one. This was a problem we ran into during development of Ray.jl, where on our CI, we would randomly see this error. And so there's two things going on here. One is there's this Ray buffer was deleted thing. This kind of indicated to us we may have messed up our reference counting, but that's kind of like a red herring. The real detail here is at the bottom, where further down the stack trace in some C output, it says check failed, expected size 28, but expected size, got data of size 17. So that we didn't really have a theory on what was going on there right away. But when we kind of dove into this a little more, it turns out that the thing it was complaining about was related to the owner address of an object. And so during the serialization process, there's a whole bunch of different pieces of information we needed. And during kind of like, we added some debug logs, and over time we realized that the problem here was that the IDs could contain null characters. And so that kind of made sense now finally why we were getting this size mismatch. So initially we ended up working around this by base 64 encoding the owner address on the C++ side, but then we wanted to look into deeper on what the actual problem here was. And so here's kind of an example of what was going on. So if you take this Julia string and you convert it into the CXX wraps standard string implementation, you get this kind of null terminated string. But then if you look at the characters inside of it, something weird's going on. That's not actually what it shows as the string. And then if we go a little further here and we go a little different, so it turns out that the C++ strings, unlike C strings, are not always null terminated. They have a number of code units associated with it, so you can actually have a length and include null characters in there if you want. So we tried using the CXX wrap interface for doing that after we learned about it, but it's still null terminated, which is a little weird. But then when we look at the actual character list, well, we suddenly see our null character, which is good, but the rest of the characters are all messed up. So what was going on here? Well, here's kind of another example. We kind of had this theory that maybe what was going on was just the display was messed up, and it wasn't actually like any characters were being messed up. But so we did a little further deep dive. So we're kind of doing this round trip between standard strings and strings. And so we said, okay, let's take our standard string with the number of endcode units, then convert it back to a string and see what the character list looks like. It's like, okay, so it's definitely null terminated here, right? That's what's going on. All right, let's do it again. This time let's take the character list from the standard string, convert it to a string, and then look at the character list. Well, we're back to our messed up character list. And then so we said, okay, another experiment. Let's take the character list of the standard string, convert it into a byte vector, then back into a string, then back into the character list, and finally we got our original data back. So it turned out the problem here ultimately was that the CXX wrap had an invalid implementations of is valid and iterate, and that was causing kind of this round trip thing to get messed up. And so it's fixed now as of CXX wrap 0.14.1, and so hooray, now you can actually do round trips between standard strings and strings. And the other thing is, though, it was kind of important to still have null terminated strings in certain cases, and so in the last little example there, if you're using a C string type, that one is still null terminated because it's supposed to be a C string, so it makes more sense. As for other things, there's a bunch of future work we want to do. One of the main ones is we want to incorporate the Julia language support into the official Ray project. We have a PR out for that. It's kind of stalled out though. It's only 200 lines of code, but the official Ray project maintainers, their kind of stance on it is they don't want to add any additional language support right now, which is unfortunate. But they did say they would reevaluate at the end of the year, so maybe we'll get somewhere there. The other thing is I'd like to make a proper JLL for this package. Array itself uses the Bazel build system, which does not play nice with Binary Builder. And Elliot last year promised me that Binary Builder 2 would solve all my problems, but at that time, during JuliaCon, he was like, I don't know if I'll even work on that. But lo and behold, it's happened, so maybe now I can fix that problem. And then some other things, just registering the package, a better high-level interface. I'd like to have some like automatic instantiation of Julia projects so you can have more of an interactive workflow with revise. And I think we can get zero-copy support in Julia using mmap, but that's something we need to look into further. And then obviously these stateless named function serialization support we'll want to add in. We'll basically probably end up using what cluster serializer ends up using, but something we also need to do. I will say that Beacon has since pivoted a little bit, so we're not working on this as actively as we used to, But I definitely want to try to push to work on this again because there's lots of interesting ideas here that I think the Julia community could end up using. There you go.
Thank you. Great talk. Two short questions. The first is, you mentioned that one disadvantage of Dagger is that it uses distributed. And what is Ray using? Is it using MPI? Can you share some light on that?
It uses its own thing. That's
Its own thing.
Yeah, so basically it has its own concept of how it kind of sets up clusters. So normally, the reason I mentioned before you need kind of Python installed is we usually end up starting the Ray cluster using the command line. That needs our Julia version language support in it. And so basically you'll start up kind of your head node and do it that way. For the multi-node support, they have a Ray clusters feature, and so we ended up using Docker containers, and that's kind of how we would like set up our initial node states. But it's kind of using its own thing, and then yeah, it's doing its own communication under the hood. And Ray itself, we're basically implementing the concept of Ray here called Ray Core, and Ray has a bunch of like machine learning training libraries built on top of that, and that's something we would eventually add in the Julia community once we had enough support for it, that kind of thing.
Sure, okay. And second short question, you had, I think the very first plot, but probably all of your scaling plots, they showed some kind of dip at, if I'm not mistaken, 50
Yeah,
segments.
like that.
Any idea what's going on there? In particular, the first one, I think it was single node. Yeah, this one.
Yeah.
Any idea what's going on there?
I'll note I didn't run these ones directly. So we probably could have just ran more samples and what was going on. It could just happen to be that like this was some weird case of like the number of nodes and workload kind of being bad. But I wouldn't normally expect this. I'd expect normally this for Ray thing flatlining behavior. So I mainly just expect those to be outliers. But like these tests took a while to end up running. So yeah, basically if we ran them enough times, we probably wouldn't see that anymore.
All right, thank you.
So just a quick question on how the workers are being set up. So there's a Ray manager on each node, right? And it does spawn the Julia workers there, right?
Yeah.
To
Yeah, so there's kind of like, there's some memory reserved for kind of like Ray managing itself, and that includes kind of that object store I talked about, and there's also just like some intercommunication setup there between the Ray stuff. I don't know the specific details of all that, because I didn't have to look into all that, but yeah, there's some memory overhead there, but it handles spawning the Julia process for you, and we did have, that's part of some of the changes we did to the Ray official code, is telling it how to spawn Julia. We ended up making it very generic such that we could tweak from the ray.jl code how the workers would end up spawning it.
okay, thank you.
Welcome.
Yeah, I think this is from the previous guy. I think he left it. Okay, super. Okay. So hello everyone, I'm Sergio Sanchez. I'm a PhD student working on quantum simulation using tensor networks on HPC at the Barcelona Supercomputing Center.
And I am Jose Giordano. I'm a research software engineer at UCL.
And we're going to present Extrae. That's a well-known HPC profiler in the HPC community, and we did the bindings to use it with Julia because it had some quirks. So this started more or less last year when I gave my presentation, and at the time I was working in Summer Cluster, and Jose was working too. He was working with the Fugaku supercomputer, and Fugaku has some quirks that Like for example, like input output is super slow, but numerical computing is super fast, and we wanted to optimize these things. And other profilers were having some kind of problems because it's not in ARM or things like that. And Extrai is developed at BSc, and it's a wild beast. It can do a lot of things. It's a little bit difficult to dominate, and it was working. We tried with Julia, and it was we were having crashes, so we had to do our own bindings for this, and we're going to present them. So the first of all is why you want to use these other profilers, these HPC profilers, that Julia's profiler has its own limitations. Julia profiler is based on periodic call stack sampling, and it can also profile multi-threading applications. And its integration with the VS Code is amazing. Like you can, it's very useful. When you have to use other profiler, it's much less pretty, let's say. And the one thing that's very nice of Julia's profiler is that it can tell you each of the different functions that you have run, if it has run a lot of garbage collection, of it was dispatched dynamically, so maybe you want to fix some type and stability, things like that. But many times there are parts where you don't know why it goes slow. Like maybe your code is type stable, it doesn't have any allocations, and still is going super slow, and you know why. And that's why, because Julia Profiler can only profile Julia in some sense. Like, it cannot profile hardware context, for example, or using other protocols like MPI. Or even if, in the end, we are using some other libraries that are writing in C, and they can do allocations too, and we cannot profile them. I think that nowadays, yes, with some part on the allocator profiler of Julia, but you cannot know like exactly which part of C. So in the end, I mean, Julia community, I think, has developed insane obsession for performance, and in HPC we have that insane obsession. We want more and more performance, and one of the questions that we have is that when we have this kind of, okay, we are having a bottleneck, is that are we really using the full power of the machine, or is that the algorithm doesn't, and we need another algorithmic change? So the first question that we have to answer is that is our code really using, is it really exploiting the architecture of the computer where we are running our applications? And for that, there are other very good profilers like Intel vTune, Liquid, Tau, Scorpy, but and Extrai, of course. We need to. So this is just one more aggregation, one more incremental improvement into the ecosystem. These other profilers have some good things and bad things. For example, if Intel vTune, it's only a thing for Intel architectures, and it's closed source. Liquid is nice, but I think that, for example, hardware counters are not very standard way of using them. Tau, I haven't used it, sorry. And Scorpio, I think, is for MPI only. I don't know. Carsten, maybe you can correct me later. I don't know right now. So Extrai, it's a provider and a tracer. It's a tracer and a sampler. Sorry. It's open source. It's developed at BSc. It predates to the 90s, where already before BSc was existing, they needed a profiler for this. And it has been in development since then. So it supports a lot of many programming models like MPI, BitP threads, OpenMP, CUDA, OpenCL, C, Java, Python, and now Julia. And also it supports many platforms. Like it can provide NVIDIA GPUs, AMD GPUs, I think so, ARM machines, Android. The K computer was, I think, the previous to the Fugaku. It has been tested in Fugaku too. Yeah, like weird architectures. Of course, it's for Linux machines, but I don't know any other supercomputer right nowadays that is not Linux, basically. And the good thing is that the tracer can do a lot of things and sampler too. Like with the tracer, you can add manual instrumentation, so if you like that way. A lot of times, we don't like adding manual instrumentation because you have to modify a huge code. So for that, you usually use LD preload. And you can trace like very used like functions, like for example, you can trace MPI calls, you can trace the CUDA runtime calls. You can also trace system calls. You can also trace memory allocation and memory freeing. You can also trace input-output. And also, just in case you don't like LD preload, there is a way where you can have this DIN-ins, that is a library for binary directed writing on dynamically, so you can actually add instrumentation without actually compiling with instrumentation. That's nice. Currently, it's not supported in our build, but I mean, it can be seen if we can add it. And also there is a statistical sampling, a periodical sampling, just like Julia. But this also allows us for, a part of the call-stack sampling, it also allows us for gathering PAPI counters. So we can have all these hardware counters and see if we are really using the cache correctly, or maybe we are having some kind of branch misprediction. And also, Xtri is extremely low overhead and has a extremely high resolution that we're gonna show later, and it generates traces for 2 other applications. So Xtri is just like the tracer. It doesn't let you see the traces. It just generates them. Then you need another applications to see them. The one is Parabird. This is the one you are mostly interested in. It's just for checking out the traces. But another one that is very interesting is DMMAS. That it's basically a network simulator, so you can run your HPC application on your supercomputer, and then if you load that trace to DMMAS, you can see that if you change like the network conditions, if you would have a speed up or not. For example, if you have a very big MPI application, you can check out that, hey, what if my network latency was 0, or if my bandwidth was infinite? Like, would that really accelerate my application? Maybe yes, maybe no. So you can actually check them out. So yeah, we wrote Xtri.jl. It's public. It's already in the general registry, and it's basically the bindings to Xtri API. So you have things like the cursor is there. So in general, it's very easy. You just need to put Xtri.init here and Xtri.finish. Many times you don't even need this if you use MPI, as I will show later. And then you can also add some regions to mark that, hey, this is a user function, so this is where my code is actually running. So that when you see the trace, you can discard all the parts where, hey, this is LLVM compiling things, or this is some kind of overhead by using benchmark tools. So you just know where it is. And fun fact, it's that the, So Xtri binaries are in Yggdrasil, so you have it built for all the MPI and CUDA versions that are available, and all the Linux versions too, and ARM I think too. And it was, as a fun fact, it was the first Yggdrasil recipe to use both CUDA and MPI platform adaptation. So don't worry about if you use any CUDA or MPI like combination, it should work. If there is any bug, yes, please contact me. And it also has some kind of preference system, just like MPI preferences. So you can actually change to use the Xtri built by the system administrators or use the one by Julia. Actually, I had better results right now with system binaries. We'll have to check that better. And also a very nice thing is that it lets you emit custom events. So if you have, for example, here, I don't know, for example, the float, like the type, you could emit an event to say, hey, I'm using this type. Or maybe, for example, the size of this vector. In those cases, so you can actually correlate other metrics like the cache misses with the size of the vector. Just a quick way of how Xtri works. So Xtri has basically three types of annotations. One are states, that they are mostly automatic, a little bit weird, but it's just they tell you, hey, right now it's initializing the application, it's running, it's doing networking, just that. It's automatically annotated. You don't have to worry about that. Then you have events. Events are just values. They are just tuples where you have some code that is a uint32, and you have the value that is a uint64. You can call register in that case. So in the trace, you will see, instead of this numeric code, you will see the string. So you know what are really what you are really seeing in the trace, not just numbers. And the last thing that you can annotate is communication. So you have some. This is also automatic in the MPI programming model, where you can see all the communication between the different ranks. There is some support for doing custom communication. We are trying to get this into distributed, so you could also see how long it's taking communications in distributed. But this requires some other improvements in the ecosystem that I will tell later. Also, Xtri is, like I say, it's a wild beast. So it has some gotchas, okay? So it doesn't always work perfectly. It's not everything so beautiful. The first thing is that Xtri has been very well thought about using LD preload, but this interacts super bad with Julia. So in the case that you're using MPI, just use, you have to put the lib Xtri inside the preload preference here. I think that Mose also needed to, in some supercomputer, also needed to add some more traces. We want to improve the MPI integration with Xtri for this, like MPI.jl. Also that the XML, it's usually configurable using XML file. You can configure it with environment variables, but it's a little bit limited. And currently we don't have an automatic generator for this. We would like to. Also that the traces are text files. These are nice because you can parse them. The bad thing is that they take huge amount of memory. I know a lot of people who have terabyte big traces in Mare Nostrum. So they are big. And sometimes when you run the application and it finishes Julia, it should run the merger, so it takes all the intermediate files to generate the trace. It doesn't always get triggered, or sometimes it has some fails. So you need to call manually the merger, but this is doable. And with this, we're gonna run some examples. And actually, Mose was with us one week, sorry. So, and I tried to teach him Paraver. It's the viewer for the traces. It's a little bit difficult to use. Xtri is nice, and it's a good thing. It's a bad thing. Is that it's super explicit. So it's a bad thing because it's difficult to enter, to start using Paraver, but it's a good thing because it allows you to do a lot of crazy things. So, do you want to try something, or should I start with something?
You start.
Okay. Okay, I will with the XP, for example. Okay, so we got to some traces here for the XP, like this kernel where you do two vector scalar product. It's a scalar product, right? It's just it's a scalar product. Okay, and also some strong and weak scaling on Lules, and also on Okami that it's an A64 FX, so it's a Fujitsu chip cluster. And also, we want some also real application. We have Trixie. So I will start with loading one of the traces. This here, Xtri traces, XP. So here, what we are going to see is that there are we're going to see XP in different, using Julia, using Bliss backend, and using OpenBlast backend. Okay, here, this one. As you see, is the interface is not the best one. It's from the 90s. It's still in development. The good thing is that okay, so when you want to see some event, you need to create this new single timeline window. I don't know if you see it. It's a little bit small. I think I can try to Okay, I don't know how to change this, so sorry. If you don't see it, I will try to put some pictures in the documentation. So when you click this, you create a new plot here where you can see the execution of all your application. The plotting goes in one thread, so don't get me to this. This is a state. you double click here, you can see this is running, and there are some parts here. As you can see, we have a huge, and this is input output probably because it's creating the traces. And what we can do is that we can, when you want to actually see an event, you have to go to the semantic. Instead of actually seeing a state, you need to go to an event, and you have different values like, okay, show me the last event that happened, or the previous next event, or just the event type. Like I said, it's very explicit. I'm going to just go for the last event value, and the problem is that now we have all the events happening here, so it's going crazy. So what we can do is we can filter by events, event type. We have to equal one of the event types. And then here we have all the different events that we actually have. And for example, I want to go for the L1 datacast missions. If I click here, then I need to reupload. I need to put again. Oh, but this is a categorical view, and I want, this is like a numerical view, like a numerical value. So I need to change the paint as, instead of code color, to grading color. And now it's okay. So as you can see here, green ones are the lowest values, and blue are the high values. So here in this time region, I'm having this little one. It's basically like, for example, here it's 3 million datacast misses in a duration of, this is 10 milliseconds, okay? But here there are a lot of things happening at the same time. So what we would like is to actually filter out all the things that are not our user code. So what we can do is put these user functions. So this is what we call our regions. And we can see here all the different user, like all the different parts. In white, they are the times, moments where we are actually running our application. This is not only white, this is a lot of small codes. As you can see, we can go very, very small. So this one, I think it's around 1 microsecond, and we have a resolution of less than 1 microsecond. So that's nice. So we will do is now derive like view, where you take these two kinds of events, and you are going to try to filter them by just multiplying, because the user functions are just binary values, 1 or 0. And we are going to call this mask L1 datacast misses, for example. Yes. And if we run this again, we change the to not null grading color, then we have it. Oopsie. So we have here all the different data cache misses for our code. As you can see here, so this is like when we grow. So what's happening here is trying 3 different element types. This is float 16, float 32, and float 64. And what we are doing here is increasing the size of the size of the vector. So at some point, you saturate the cache, and you have a huge amount of data cache misses. And actually, we can actually check out what's the value of these lengths. So we could actually create event. Again, I know this is a little bit too verbose. It is. And now I'm going to check the... I think it... here, sorry, the first one. Yeah, vector length. Here again, I have to change this. The good thing is that you can save your events, as Mose will show. Paint as grading color. Yeah, here. So you can see here that if we actually expand this, that in this case, we start having problems around here. That it's around when we have a size of 63 million elements in a vector, more or less. You can also save maybe the bytes or multiply this. Okay, now I'm going to pass.
Do you have the traces that I sent you?
Yes, here in Okami. Okay. Just load trace, yeah.
Yeah, no, I wanted to show that you can save the session, which is very useful.
Yes.
Because, yeah, you see that you basically need your window, which is a bit painful the first time that you do, but then you can save the session so you can remember all the settings, like all the views that, that you created. And how do I load it?
Here, oopsie. File load trace.
Both.
Here, and extract traces here in Okami. You have them here.
Okay, and then the session.
Load the session. Let me see if we can load this. Okay.
And so you can actually load both the configuration, or like once you create your own visualization, like I don't know, the vector length, or the other window was for the cache misses.
We have a problem.
Okay, okay, but the point is, once you create your visualization, you can save the configuration of that window, and also of the entire session, like the entire paraver session, and then hopefully, I don't know, you can reload it afterwards, so that you don't need every time to like recreate the individual windows manually.
Okay.
As you can see, live demo is always super cool.
Sorry.
Right.
On that topic, Mose, is the session independent of the trace file that I'm loading? And then maybe apply it to different runs?
So the configuration is the configuration is independent. I'm not sure about.
No, the sessions you need the traces, but what you can do is save your custom filters for the events. Yeah. You can save that into configuration files. Yep. Yeah, you need to. Yeah, he ran in another computer. That's why. And again, I think.
So the session was invalid, I guess.
Yeah.
Okay.
Sorry, the session was invalid, but I think you need to now to. Okay, put them here in this. Like it's the grace and the AC64FX.
Yeah, I mean.
Traces. Okay, to just copy them here. And let's hope that this works. Okay, let's try it now.
But yeah, definitely the first time that you use Paraver, it takes some time to get the configuration, and it took me like 1 day to learn it. But then when you can save the configuration of the window that you generate, that's much easier for the future, which is what we wanted to show. It's not going very well now, but no. I can tell you it will work eventually.
I think you need to load them. Sorry, you need to load them manually. Sorry about that. Okay, here.
Especially if you do on the same machine, because we did the mistake of moving from my machine to his machine, and now it's not loading.
Yeah. Okay, and this is the. Okay, super. This is Grace. The good thing is that you now have the traces and you have the.
It works.
Yeah, the traces
and
work.
The trace works and the
configuration files.
Yeah, very quickly. Or anyway, there is the hint. Like in hint, we can show at least the IPC count.
For example.
Yes. So another thing is that there are some pre-built configurations that you can show, and this is, for example, the IPC count, the instructions per cycle count. And you can see, so I think this program was running a matrix multiplication, and we wanted to see how many instructions per cycles there were, and yeah, to see the values here.
Yeah, it's a small, but it's you click in one part of the plot, you see that it's right now it's like around 2, like the blue part is 2.
Yeah, so this was on A64FX, and we have traces for comparing A64FX and NVIDIA Grace, which are both ARM CPUs using the SV instructions. And Yeah, okay. So now we don't have much time to go on with this comparison, but yeah, you can have these plots and put them side by side or on top of each other to compare the IPC count and see how many instructions per cycle you're spending in your operations. Do you want to
Yeah, I
say?
wanted just to finish because we don't have much time. I wanted to show one execution with MPI, so you can see also. This. Like for example, this one with. So this is this is a execution of Lules. It's a HPC application coded in Julia, and it's calling out of MPI. This has 64 nodes, and you can see them here. Each color here is a different MPI call. So for example, these red ones are MPI barrier, this green is MPI init, and here where all the computation is actually happening, you see there is all, pink is all reduced, and the other are basically weight. And you can see also, whoopsie, you can also see the communication lines. So here is now a mess, but when you're waiting, you can see that which one is waiting to which here. And also you have some other hints, like for example, getting the MPI size, MPI profile. So here, for example, we do this, we can see which MPI application, which MPI calls are the ones that are taking more time. So for this application, it's 72% of the time it's actually doing other things outside of MPI. But afterwards, it's around, it's MPI weight that's taking a 10% more or less, and also MPI barrier is taking another 10%. And to finish, I would like to just say that there are a lot of things to do. We are working on, on some integration with trace points. Please, we need help with trace points. It's basically a package that we are trying to get, so we have a standard for instrumentation. So if you want this working more seamlessly with Julia, please help us out. Tomorrow, Julian will be around hackathon, so you can contact him if you're interested. We also have to test CUDA instrumentation. So CUDA works with Xtri. It's that we couldn't test it with Julia applications. We didn't have time. All the ones that we try, they crash it because of other things, not because of Xtri. And also that we would like to maybe try it with other applications. So thank you all.
Is there any questions?
Thanks, great talk. Obviously, I have lots of questions, but most of them we'll take offline. Let me start with one or two. So first is, you showed Parava for visualization. Can you convert the trace files that X-Ray produces to other formats, like open trace format or something? Because that would give you access to more visualization tools. As you said, it's from the 90s, it works, but I don't know.
I haven't seen it. I like once I found out that maybe someone had some converter. I haven't found it again. The good thing is that it's a text file. It's very easy to parse it, so it should be doable. I'm currently working on that to add a parser to the package.
Sure. Yeah. And second question, then I'll leave it for someone else. You showed the timeline view, like traces, where the timeline is obviously the main focus. What about sampling results? Where maybe I don't care about the time resolution. I just want to see, where in my code is most of my time spent. X-Ray obviously has that feature, right? Sampling. Yeah. Have you tested that? How do you visualize it? Is it also Parava or some other tool?
You use these kind of things, like these things. So this is, let me show it. Oh, no. Wait. It's a little bit hard to. Basically, this is an histogram. You have to use these kind of things. So you have the x-axis is one of the plots, one of the timelines, and the y-axis is another of the timelines, and you correlate them. And you can also add a third plot timeline for the color. So you correlate them. It's not the best way. Like you would like to have some other fancier plots. In those cases, what they do, it's you can take here and save it as a CSV file, so text file, and then you process it manually. And officially, there is something going on to have better plots, but it's not. It's like it's very preliminary.
Fair enough.
Any other question? No? I think, thank you.
And if you're interested in HPC, come to the booth.
Yep. Pero como esto, claro, en el Computer Science Julia no lo... Y entonces...
No, bueno, lo digo para la herramienta esta y el para ver y todo esto. Enrique Tejero había trabajado en el centro de cálculo en el computer.
Sí.
Entonces, cuando vino a nuestro grupo, pues empezó a usar estas
Sí, sí. A ver, es que me dio clase de Jesús Labarca.
Me suena.
Uno de los que empezó a crear esto y tal, y el jefe del departamento de Computer Science. Sí, sí.
Está bien, muy bien.
Bueno, encantado.
Vale, gracias.
Yeah, perfect. So I think we are ready to start. Yeah, thank you very much and welcome everyone to this presentation. I am Francesc Verdugo and come from VU Amsterdam, and today I'm going to talk about partition arrays and in particular one of the latest developments in this library, which is about parallel algebraic multigrid preconditioners. So this is a rather complex piece of software, so let's start simple, right? So imagine that you want to solve a system of linear equations in which the matrix is a sparse matrix. For instance, this is this particular instance here. If you want to do so in your laptop with Julia, it's straightforward. You go to partition to sparse arrays. You have the sparse function to build your sparse matrix, and then you can use / to solve the system. And under the hood, you're going to use a direct sparse method implemented in C. I think it's umfpack, the method that's being called under the hood. But of course, in real world, we want to solve much challenging problems, right? So this type of sparse systems result from the discretization of PDEs in challenging applications from 3D printing to photonics, etc. And in these cases, you have equations with millions, tens of millions, or even billions of rows of unknowns, and you cannot use your laptop to solve this problem. So your laptop and / is not going to be sufficient to solve these applications. And here you need a supercomputer and a library that allows you to distribute all these sparse matrices and vectors, and also a library that provides solvers to solve these systems in parallel. And this is what partition arrays tries to do. Okay, so it's a library that provides distributed vectors and sparse matrices, and on top of these, solvers to solve these type of systems. You can ask, okay, so this is already done in other packages. So there are very famous packages such as Petsy, Trelinos, Hypre that provide also sparse linear solvers. But our package has two main features. First of all, it's implemented in Julia. It's fully implemented in Julia. I think it's one of the such a library that is implemented in Julia. But of course, it's not the key novelty. I think there is another nice feature of the library, which is that it's implementing using an alternative programming model that decouples the parallel logic from the parallel execution of your problem, which greatly helps in the developing and debugging of your applications. And so this might sound a bit abstract, right? So you have a small example here, a very simple hello world example. Here, the goal is to build a vector of length 9 distributed over 3 parts with these particular values. Here, each one of the colors represents one of the parts that eventually you can think of that each one of these parts is going to be mapped into an MPI rank in a distributed machine. And this is the code that does this with partition arrays. And so I don't want to go into details, but the key idea is that you can, so this is running in a Jupyter notebook, so it's running in sequential, right? But still you see how the data is partitioned. If you look here into the local values of V on the right-hand side, you will see that V is being partitioned, and you can see how the data is partitioned. So you're able to see which is the logic of your parallel application, even though it's running in a Jupyter notebook, it's running in sequential. Of course, once everything works and you are happy with your code and you have a prototype working, you can put all this code into a main function and then use a small extra functional call here at the bottom with MPI. And now we change the backend and we run this with MPI. And this file now is an MPI application that you can launch without MPI exec, and in this particular case with three ranks, and it's going to run on your supercomputer. How does it work? So the key idea is that partition arrays is not implemented using MPI directly. We have a layer of parallel primitives on top of MPI, and we have two implementations of these primitives. We have an MPI one for deployment in the supercomputer, but we also have a sequential one for testing in your laptop and for prototyping. And yeah, so implementing the MPI implementation is straightforward because there is almost a one-to-one mapping between our primitives from and the MPI primitives, but implementing the serial ones is a bit more challenging because you need to think of a new approach, right? And here the approach that we follow is that all these primitives can be thought as operations on arrays. For instance, MPI gather, in its simplest form, MPI gather, you start with one item at each one of your MPI ranks, and you want to collect all this data in a single MPI rank, right? And this is the array abstraction that we are using here. So we think about this operation that you start with an array V in which each one of the items of this array is distributed over the ranks, and the output is an array of arrays in which all the data is in the first subarray. And you can formalize this with this formula, which of course could also be implemented for a standard sequential Julia arrays, and that's how we were able to implement the sequential backend. And this is how it works for a standard sequential array, right? So you have a vector, you call gather, and you have all the data in the first subvector. And now, if you go to MPI, which is the picture on the right-hand side, here under the hood, you're going to have an MPI gather. Okay, so you're going to start with these 3 items, each one in one MPI rank, and then you're going to gather all the data in the first MPI API rank. So we have a lot of different parallel primitives, and we have several layers, right? So if we start with parallel primitive, which is the lowest layer of the software. On top of this, we have the linear algebra kernels. We have P vector, which is a distributed vector. We have P sparse matrix, which is a distributed sparse matrix. And we also have the usual linear algebra kernels, a sparse matrix vector product, a sparse matrix vectors product, reduction, norms, etc. And on top of this, we have a new layer now. We are starting working on sparse solvers. And we have a first implementation of a distributed algebraic multigrid preconditioner, okay? And even on top of this, so we were also able to implement distributed finite element codes. So in particular, the grid distributed package is using under the hood partition arrays in order to assemble the finite element systems in parallel. So if you are using grid distributed, under the hood, you're using partition arrays to do all the data partitioning. Yeah. This is how this is our first prototype for the algebraic multigrid. So as you know, algebraic multigrid methods are infamous for having many parameters, and this is the way we specify the parameters. So the first block of code, we specify the parameters for a single level in the multigrid levels. Here we are using an additive Schwartz plus a Gauss-Seidel as a smoother. We are using a smooth aggregation for the coarsening, and the cycle is a V-cycle, and you can choose also different pre-smoother and post-smoother. Then we fill a vector of level parameters so that we have one set of parameters for each level. So you could also customize all the parameters for a per level basis. And we also have the coarse level parameters. In this case, we are using the LU decomposition that we have in base. Yeah, so you use these parameters, you have your AMG solver. And now if you want to use this system of linear equations, you set up the solver, right? And you can now use it to solve the problem. And you have three different flavors here, solve. The first one is going to use the data in X as initial guess. So if you have an initial X, solve bang is going to use this initial guess. LDiff is going to ignore the initial guess. It's going to assume that the initial guess is 0. And this is the function that we use for the preconditioner, actually. And you can also use this setup, the object that we generated in the setup, as preconditioner in other solvers, for instance, in conjugate gradients in iterative solvers.jl. So it's able to integrate also with other Julia packages. To finish, maybe some words about performance. We are improving the performance. We want to work on this. And there are some preliminary results for the sparse matrix vector product, which is one of the key computational bottlenecks of iterative methods and multi-grid methods in general. And here I'm comparing partition arrays against PETSI for doing a strong scaling test for different problem sizes. And as you can see, for a large problem size, both libraries, so partition arrays is as fast as PETSI, more or less. Yeah, but for the smallest problem size, I think there is some room for improvement, because we are up to 3 times slower than PETSI. So I think this is related with the way that we do latency hiding. We are spawning Julia tasks, and it's hitting some overhead, and we have some plans to avoid this in the future and try to be as fast as PETSI also for the smallest problem sizes. Yeah, as future work, we want to extend this to multi-GPUs. We want to continue working on more preconditioners, including domain decomposition preconditioners. And another interesting extension will be to distributed dense arrays, multidimensional dense arrays. Now we have the distributed vector and the distributed sparse matrix, but we want also to add like multidimensional distributed arrays, which is going to be also useful for people working, for instance, infinite differences, etc. I think that's all. So I'm here to answer your questions. Thank you.
Any questions?
If we want to write a package that is compatible with a partition array, is there an interface that we need to satisfy or a minimal set of functions?
So you want to use partition arrays, right?
Oh, I want to let the user decide if he can use this type of arrays inside, for example, my package.
Yeah. Yeah, the p-sparse matrix and the p-vector, these ones implement the Julia array interface, except for indexing. So this is a bit strange. You cannot index a p-vector on a p-sparse matrix, because in general, this would require communication, right? So we have disallowed indexing for this reason. But for instance, if you have a p-sparse matrix and a p-vector and you multiply them, automatically you're going to dispatch to a parallel version. So if you use all the usual array operations, except for indexing, is going to work. Yeah. I mean, if you're using indexing, it means that you are writing a sequential algorithm. That's why it's not going to work in parallel. But if you write your algorithms in terms of functions that have been parallelized in partition arrays, then it's going to work. Yeah, you need to be careful. It's not like for free. It's not 100% for free, yeah. Yeah, it's a Julia interface. So it's the Julia array interface except for indexing. Yeah.
Thank you.
For coming. I'll be talking for 10 minutes about trustworthy AI in Julia and how it meets supercomputing. For those of you who have never heard about Taija, it's a small and growing ecosystem for doing various things like explainable AI, conformal prediction, which is a way to quantify predictive uncertainty. Laplace Redux is a package for Bayesian deep learning. And then we have recent joiner, joint energy models, which is an approach to hybrid modeling. This package, Taija Parallel, is one of our meta packages, and it adds support for various kinds of parallelization to certain Taija packages. The focus was on having an intuitive user interface, so to minimize the cognitive load on users, to add support for both multi-threading and multi-processing, and to make it easy to extend the parallelization methods to new packages that might arrive and new functions. Why do we even need this? So one of the drawbacks of trustworthy AI and all the methods that people have proposed is that they tend to increase the computational burden. So to give you some examples, in explainable AI, we might often need to generate explanations for multiple people, for multiple individuals that are affected by algorithms. Conformal prediction, one of our packages, often involves cross-validation or bootstrapping. We also have Bayesian or quasi-Bayesian methods like deep ensembles that essentially all involve tasks that can be easily parallelized. As a motivating example, so this package was really developed to support research that we presented earlier this year at AAAI, which involved generating large benchmarks or running large benchmarks of counterfactual explanations. And I had a different talk yesterday where I presented a bit more detail on this paper here. We essentially worked on trying to find a way to generate model explanations that faithfully explain model behavior. And to test our methods rigorously, we ended up running, just in the final experiments, a total of roughly 10 million counterfactuals. And this was parallelized across many CPUs, probably more than we needed ultimately, but we used our supercomputer. And the Taija Parallel package was used as the backend. yeah, if you want to look at the code for the paper, it has its own small package, echo.jl, which extends existing packages in our ecosystem. But to be conscious of time, just to look at what Taija Parallel actually offers. So I'm actually quite new to parallel computing. So even though Julia makes it incredibly easy for newbies like me to do these things, I thought, okay, can I minimize the cognitive load for students that are working with our packages, for example, even more? And that was really the goal here. So we really now on the user-facing side have only this one macro with parallelizer, which makes it easy to parallelize many of our functions. So here we have pretty much the main API call of our counterfactual explanations package, which generates for some factual samples counterfactuals in a target class for a given data set, a black box model, and a counterfactual generator. And all you need to do if you want to actually parallelize that computation is to use the simple macro, so with parallelizer, and here I've instantiated previously an MPI parallelizer, and then we have this begin, end block, and then just the function call. So it's really, really easy now. Under the hood, what's happening is that we have this Taija base package, which ships some common symbols for our packages. So this one adds the basic functions, like a parallelize function and an abstract type for parallelizers. This is handled in Taija base so that other meta packages and core packages can call this functionality without actually implementing the computations. Taija Parallel is then the package that adds the support, and out of the box it adds support for multi-threading. If users want to use something like MPI for multiprocessing, then this is handled through a package extension to minimize the loading times. And I think, being conscious of time, I won't go into too much detail here, but just to say that it's also very easy to extend these methods because they're dispatched on different parallelizer types. So right now we have a threads parallelizer, which then enables multi-threading, and an MPI parallelizer, which enables multiprocessing. So there's a lot of room for extending the scope here. And it's also possible to combine different forms of parallelization in a single function. One caveat is that the functions that can be parallelized are expected to be broadcastable. So we always expect that, such as in the case of generate counterfactual, that the arguments that go into the function can be split into different chunks, and then the operations can be run over these chunks. And yeah, just one final example on timings here. Yesterday I played with this a little bit because I haven't really run performance benchmarks on this package for a while. And now, after going through some profiling and with the simple threads parallelizer, we can generate 10,000 counterfactuals for the MNIST data set on a MacBook using multi-threading in under 2 seconds, which might not mean much to anyone who's not working in this space, but to me this was really cool. So with that, I'll open up to questions if there are any.
Any questions?
Thank you so much for the talk. That was great. I'm also kind of working in a trustworthy, fair AI space, and it's nice to finally hear a talk about it. So it's been great. Thank you. I wanted to ask if you've been kind of looking at Dagger and where that's been going, and whether you're looking at supporting Dagger with your own work.
I haven't yet, but I've heard a lot about Dagger at this conference. So I've been planning already in my mind to maybe go there. Yeah, okay. Sounds like a good idea.
Thanks.
Yes. All right. Thank you.
Thank you.
Cheers.
Thank you. So thank you very much. So at last year's JuliaCon, I started with an example showing our package, an example simulation showing the breaking of spaghetti. So for this year, I thought maybe I will start with a similar example from the kitchen you can all try out at home. So basically what you can see here is a simulation we've done with our package on glass falling to the ground and breaking into many pieces. So let me comment this. This was a saying from my wife's grandfather. Falling is not a problem, but hitting the ground is. And this is especially true when you want to simulate that with a numerical framework, because it's very hard to obtain all these different fracture elements, and yeah, it's very hard, but with pair dynamics you can do that. It's very suitable and very suited for these kind of dynamic fracture simulations. So what is my talk about? I want to start with a short introduction. What is pair dynamics? So introduce you to the main equations. And then I want to go on with what is our pair dynamics package and introduce that a little bit if you don't know it currently. And then I want to focus on the API improvements, so basically the public user interface, and then also on recent performance improvements we've made. So basically the internal side of the package. So to begin with, what is pair dynamics is basically a non-local formulation of continuum mechanics. Basically the body is discretized often by points, but it could in theory also be discretized by a mesh, but it's a non-local method, so these points interact only inside a specific horizon, so inside of a specified radius around a root point. So basically when you model in kinematics with that framework, it's basically you look at these interactions, these bonds. Here you can see it as x and x prime. So to introduce a little bit notation, if you want, you look at the deformation. Like in classical continuum mechanics, you refer to the reference configuration so basically the time step 0, and then at the current configuration, the deformed body. And if you look at reference position coordinates, you refer them as with uppercase letters, capital X, and in the current position with lowercase letters. So basically, the main equation we solve is the equation of motion from pair dynamics. You have here the density, the acceleration, and the internal and external force densities. And in this internal force density is very important because many different formulations exist that differ regarding that. So the different material formulations differ in regards of the calculation of this internal force density. So if you want to calculate that, basically you have to look at these force vector states you can see on the right side of the picture. Basically T and T prime. These are mainly then differently calculated in the different backends or different formulations of pair dynamics. They can be of the same value and in opposite direction for bond-based pair dynamics, but that is not the case for ordinary or non-ordinary state-based pair dynamics. What I just want to say with this slide is there are many different implementations of pair dynamic formulations, and it's very difficult to implement them. It's not the same way. And basically that was the main motivation for me to use Julia for writing pair dynamic simulations, because it was much easier to implement these different approaches. So what is pairdynamics.jl? It's a registered Julia package. You can see the GitHub page with this QR code, and it's purely written in Julia. So basically the goals of this package are mainly to make pair dynamic simulations accessible for a broader user base. And for me, it was also a reason to implement these, because new material models was very hard to implement for me, and it could be made easier for other people too if there's a Julia package. There are also packages out there in C++ or other languages, but they're very hard to use. And you can write Julia code to obtain a simulation with this package. So I want to show a short usage example. So this is a very common example or simulation in mechanical engineering. You have this tensile test specimen, which then is subjected to tension at the bottom and the top. And basically, you can use just these lines of code for a simulation with our package. Here, you first construct a body, and then at this body, you specify the material formulation. Currently, 4 formulations are available in our package. And what you can do then, you can import abacus measures into the simulation. Then the element will be converted to a point. You can specify material parameters to that body, then boundary conditions, and actually you can define element sets inside of abacus, and these sets will be recognized and converted to point sets here in the package. So you can specify the boundary conditions using these sets, and then you specify a solver and can obtain simulation results with submit job. So basically, if we look at the simulation here, it's what we would expect. This specimen is subjected to tension, and in the middle of the specimen there a crack is forming. So this is basically a dynamic simulation with fracture involved, but you can also do a different kind of simulation with just a few changes. This is a different setup, so basically the same point cloud, the same spatial discretization, but with different conditions. So we have here force density conditions. Basically, we apply a constant force at the top and the bottom, and we disallow failure, so failure should not occur in the model. And we use other solver. And if we look at the simulation here, you can see it's with just a few changes we obtained a quasi-static simulation, just the elongation of this specimen under load. So basically, these things are implemented. What I showed you are the current version. If we compare it to the previous version, it was much more code, but everything was a separate struct in the previous version. So the material was a separate struct, the boundary conditions were a struct, settings, and also the analysis. And then at the end, all these things would get bundled up together for a job to submit. In the current version, it's a little bit different. So it's not just only less code, and I think, in my opinion, a little bit easier to read. So methods add something to a struct. So this allows us to write more meaningful error checks. I will show you that here. So basically that's an old code, and we introduce an error purposefully. So we introduce here a boundary condition that references point ID 1001, but with a body that only has 1000 points. So basically when you construct or bundle these things up, this would be the first time this error could be detected. But because if you disallow bound checking, the simulation will also run completely, but then you will get NaN values. And I ended up helping our students a lot of times searching for errors in the user input. So we improved that. In the current version, you can only add things via a point set. And if you try to add a point set for points that are not there, there's immediately an error, because we already know when specifying these point sets, adding these into the body, that there are not more than 1000 points. So basically, if a job can be created, it is likely that it will run without input errors, because per user error. So every possible check is done as early as possible. So there's a new setup. It's a bit lagging on my computer. So there's a new type of setup for these simulations. Basically, you first construct a spatial setup. So basically, for single body simulations, you just create a body object and add everything that also is dependent or important for that body. After that, you add a abstract time solver. Basically, currently 2 are implemented. And then these things get bundled up to a job. So, and for multi-body simulations, this even helps because it was a mess in the previous version. You needed a lot of intermediate structs, but now you can construct the bodies at the same you would do for a single body simulation, and these will get bundled up to a multi-body setup. Then you add the contact, just do that setup. And then again, you specify a solver, and it will get bundled up for a job. So now we will focus more on the performance, or basically the internals. That was kind of the user interface, but how do we use parallel simulations? So if we use that same example, it's basically, you can run that on parallel using multiple threads. You just have to start Julia with more than one thread, and then it will automatically run on multiple threads. But what you also can do now with the current version, you just can run it, put it in a script, and run that script with MPI, and without any code changes, the simulation will run with MPI. So basically, the parallel backend is automatically detected, and then the backend will be used for the simulations. So what is the performance of that? So performance was always a thing for this package in the previous version, but let me introduce a short benchmark I always use. I don't want to go in detail on how this code works. You can basically copy that and try it out on your machine. So basically that are 1,000 points or 100,000 points for this setup, and the simulation completes after roughly 20 seconds on my machine. But the main thing, how is the HPC performance of the package? So if you look at the speed up of the previous version, the multi-threading in version 0.2, basically what you can see in this plot is my realization that parallel processing on an HPC system is not just add threads to a for loop. It's much more complicated than that. So why was this slow? Here you can see the important code, the bottleneck of the simulations, the force density computation. And in the previous version, basically what we did was we looped parallel over all threads to create a thread ID, and then had a pre-partitioned bond vector array that contained all bonds for this thread. And then this internal force density, BINT, is basically a 3-dimensional vector and array, and each thread writes on its own dimension. So, and then after that, we would need a reduction. The error with that is force sharing. So I think there are a lot of people here at JuliaCon who could explain that better than me. But basically, because all threads use the same array here, the cache line will get updated for every thread if something is written in that. And therefore, that's a small overhead. So we basically need a new data structure for our data to be stored. And what we did, we completely redesigned the package. So basically, under the hood, nothing is, not a single function was the same in the previous version. So now we use a body and split this body apart into body chunks. So what you can see here is basically then we need communication. So we have these local points that are local to the body chunk, but also some points of the other chunk. Here you can see the green and blue interface points, the halo points, are needed for that chunk to, for the computation. So basically then you need communication. There are two types, basically local to halo communication. So data that is calculated on here, the local points, needs to be updated into the halo area of another chunk. And also the other way around, so halo to local exchange. So data that is calculated on the halo points, just in the simulation, the index J, that data has to be then exchanged to the other local points of the other body chunk. So basically, this needs communication, but the same approach is used for multi-threading and MPI in our package. So everything happens on a body chunk. This is basically the type that makes it possible to write these two backends without writing everything for two versions of the package. So basically, the body chunk contains material information. That is mainly the material formulation type, which can be used for multiple dispatch. Then the point parameters, like the density, Young's modulus, post-source ratio, and other material parameters that can differ for each point. And then a system with all reference configuration informations, the neighbor informations, and a storage, which then is basically everything that will change during the simulation. So displacement, velocity, acceleration, and so on. So this allows reusing methods that work on a body chunk with multi-threading and with MPI, because they both use this type. So then we need a threads or a MPI data handler. Basically, a threads data handler contains multiple body chunks. And then you need halo exchange information. And compared to that, an MPI data handler only has one body chunk, but also needs the same halo exchange information and additionally some MPI stuff. So basically, the core functions that or core methods on these body chunks or halo exchanges can be reused with both backends. So how does this internal structure change the HPC performance? You can see the scaling of multi-threading in the current version was greatly improved, and not only because of this data structure, but also strongly because of thread pinning. It's a great package to pin threads to specific cores or NUMA domains on a cluster. You can look it up. There was a great talk at last year's JuliaCon. It's a package from Carsten Bauer. And if you look at the MPI simulation, it scales very well. So if you look at the highest point here, it's roughly 800,000 points, and with 46 MPI ranks, that simulation will take only 65 seconds. So basically, this wouldn't be possible without the help of the Paderborn Center of Parallel Computing. So I really want to acknowledge the support of Carsten Bauer and Jin Wu, who invited me to a hackathon, and there we created the basic foundations, the core concepts on how this package can improve the parallel performance. So a little bit different is the performance for multi-body simulations, because there you have additional things that needs to be considered, because if these bodies move, then you need a contact search algorithm, because these points are not always in contact. And if these points are nearer to another or are lower than a specific radius, then there's a contact. And to obtain these information, it's important that you have an updated neighborhood search. And here I want to acknowledge especially the Trixie Particle guys who wrote a very nice package. There was also a talk on that on Wednesday, so you can check that out on YouTube. And it really helped me to obtain performance increase in these kind of simulations. So if we look at the benchmark, the old Paradynamics logo, this took, in the previous version on my computer, around 115 seconds. And now it only takes around 23 seconds, just because of these internal changes and also the updated neighborhood search. But keep in mind, it's currently only available for multi-threading support, so it's work in progress to add MPI support for this in the future. So things that can be improved further. So basically, the spatial decomposition is currently very trivial. We don't have a suitable decomposition algorithm yet. That would be a thing that could improve MPI performance very much. Additionally, other material models will be a nice add-on that that don't have the pitfalls of the current models implemented. And also a thing currently only, I think for package developers or for me, it's easier to implement new models because there is no public API for defining new material models. And it would be very nice to have public macros to define a new model. Under the hood, in the internals, I already use some of these macros. So this is basically a copy from the current source code. If we create a storage for a specific material and a specific solver, you can specify that it belongs to that with this add storage macro. And if you want to specify which fields need an halo exchange, you can do that also with this one line, with this macro. So basically improving that and maturing that interface could help to gain a public API in the future. And one more thing, the Trixie Particle guys and we sat together yesterday to try to visualize this glass simulation with Blender. So basically they do fluid simulations, and because we are not an expert in Blender, we just had to reuse their material, so it just currently looks like a water glass, but it will likely improve in the future. But the main thing I want to show is they have really great algorithms for improving the point clouds. So basically they helped me yesterday to improve from a cloud looking like that was basically converted from a finite element mesh to a very good point cloud with a smooth boundary or smooth surface. So check out their package, it's really great. So what I think we could add maybe is fluid-solid interaction with paradynamics. So maybe next year we can show the glass full with wine. So with that, I want to end my talk, and thank you very much for your attention.
Any questions?
Could you explain a bit more on why there's a difference in performance of multi-thread and MPI stuff, since I don't really get it.
So you basically want why there's a performance difference here in... Okay, so I think this could be related to many things. It's very sensitive to the setup of the parallel of the setup on the cluster. So I once had a simulation where I just included a recursive remove of previous results, and that would change the it completely. So actually, I'm not very sure about the details of that. It could be setup, but it could also be just because they are under the hood completely differently using the communication. One is via the MPI interface, and the other approach is using basically just use at this point information to that into the same vector. So maybe that would be the reason, but I think I'm not very good at explaining that because I'm more at the application side of using Julia, not on the HPC setup expert side. So maybe that's a good question for some people of the HPC community, but I'm not quite sure. Yeah.
Thank you.
Very great talk, thank you. You showed your benchmark setup, like displayed, and then also your MPI results, like it took about 50 seconds for 800,000 particles.
Yes.
So how many time steps did you simulate?
At each time, I fixed the number to 2,000 time steps.
Ah, okay.
So to compare basically the implementation, I think with 800,000 points, I probably would need more time steps to see the same simulation results, because if we have increase the number of points, the time step you would need for the velocity Vallée solver also decreases. So you need more time steps to cover the same time interval of the simulation. So, but this simulation results with MPI on the cluster were obtained by just with 2,000 time steps.
Cool, thank you.
Other questions? Thank you. All right, everyone, let's start this afternoon's session. Our first speaker is Firuzi from Fraunhofer. She's specialized in computer algebra systems, and today she will tell us how Julia drives the development of high-performance computing tools.
So, hi, everyone. Thank you for being here. Thanks for the nice introduction. And before I continue, disclaimer, if anyone wants to already start digging into our code and opening up issues on GitHub, that's the QR code you want to follow. And if you want to follow the slides live with me, the QR code down there should take you to the Google Slides link. And hopefully I didn't mix up the two QR codes, but you would see at least the GitHub one at a later stage as well. So again, welcome. I'm going to talk about distributed workflow.jl. This is a fairly new package in Julia, which is trying to interface a distributed workflow manager so that you don't have to leave Julia, preferably, for as long as possible. Okay. So before I introduce the package, let me introduce the main characters who were involved in this package. So I am a PhD student. I started my PhD at Fraunhofer on a stipend, which is where I came across the underlying distributed workflow management system. By profession, I am a theoretical mathematician, an algebraic and tropical geometer. So very, very domain-specific research. And I'm associated with the RPTU University in Kaiserslautern. So how did I get introduced to Julia in the first place? It was peak of the pandemic. I started my PhD, and I had to now suddenly learn about computer algebra systems, specifically in Julia. And the specific one I was working with, or trying to learn, is called Oscar. I am not sure if people have heard of it, but it's fairly well known amongst mathematicians. And with whatever documentation that was available, I started learning about Oscar and how to use Julia and different features of Julia and Oscar. And at the same time, I started working on understanding the underlying workflow management system and how to use it. Not being a computer scientist, I would say both these two aspects were a steep curve for me. I'm comfortable with one. I won't tell you which one now, but maybe you'll find out yourself. So before moving on, again, let me get some of the basic definitions out of the way. What is a distributed workflow manager? According to Wikipedia, a workflow management system provides an infrastructure for the setup, performance, and monitoring of a defined sequence of tasks arranged as a workflow application. Luckily, the underlying theoretical basis of the workflow management system is based on the mathematical concepts of Petri nets. So that got me very excited. I was like, yay, Petri nets, I know what they are. So what are Petri nets? A Petri net is a directed bipartite graph that has two types of elements called places and transitions. The circular objects you see on the right of the screen are known as the places, and the rectangular boxes are the transitions, and they are connected to each other through an arc. No two places can connect to each other unless they go through a transition, hence bipartite graph. And I was like, cool, I understand this. This is very easy as a mathematician. What's the problem? Well, the implementation of it. So, okay. Then I started learning about how to use the underlying workflow manager on its own, because I need to understand that before I can use it in my research. So what would be the steps involved in writing a hello world example, which is a very basic, simple place, transition place, where the input place goes into the transition, does some hello world thing, and gives you an output token or an output result that you can read. So the first step is you have to come up with an application structure for your initial application. Then we have to create an executor, design the workflow, because it's based on Petri nets. That is what would launch later on. Create your workflow launcher, because the workflow needs to know how to launch it. And compile and execute. 5 easy steps. What's the problem there? I wouldn't go into the details of all the 5 steps because we are here to talk about distributed workflow.jl and not the underlying workflow manager, but I would still like to show you the first 2 steps, how to set up the application structure and how to create the executor. And I would like to remind you at this point that this is pure C++ code. There's no Julia involved at this point. So we start with a simple main CPP file. Okay, you can read the contents or you can read it later on the Google Slides, no problem, or on their how to use page. There is some more information coming in and maybe some more. And yeah, so these were the first 2 steps. And if right now you want to run away from this room, I don't blame you, but hang in there. I promise things are going to change. So as I said, these are the first 2 steps. We haven't even designed the workflow yet. And if you're scared of C++, I introduce you to the Petri net, which you have to write as a XML file yourself manually. You can still do it if you're like, yeah, this package sounds like it's for noobs. I can work on it myself. Why do I need this package? I encourage you to go ahead. I don't have any problems with it. But for others like me who are scared of everything that you saw, and the first time I saw all of this and I understood how to use it, this was pretty much my reaction. Emotional damage. And if I've caused emotional damage here, I'm sorry for that, but as I said, things are about to change. So, what were my frequently asked questions to my project and PhD supervisor constantly when I was learning how to do this? Number 1, do I have to write this over and over again for each new application? That was just hello world. And can't I simplify the interface to make it easy to use for people like me or others who are not computer scientists? The answer to the first one is yes. So you have to write it again, and the complexity increases with the larger your workflow becomes. Luckily for us, the answer to the second question is also yes. So introducing to you distributed workflow.jl. However, currently we have some small initial setup that we have to do before I dive into the Julia code. So you would require at the moment a spec installation. If you already have it, you can skip step number 1. Otherwise, you can go to their getting started page and set it up. Next, you can go to our GitHub repository, download the respective binary from our release tag for your appropriate Linux distribution. Extract the binaries in a target location. Here I call it Zeta. You are free to call it whatever you like. It is the location where all your binaries will be extracted. And hopefully everything goes well and the computer science gods are not angry with me yet. We can do a spec load and the binaries are loaded and we are ready to use. We are ready to use the package. And I'm so glad I came to this conference this year because I got to meet a lot of HPC experts, Julia HPC experts, and binary builder experts. So if what I heard and learned from them works out for me, I have to try it out. If I manage to build it with the binary builder, this step will be removed for you entirely, and you can do exactly, you can download the package exactly how you download any other Julia package. So for now, minor inconvenience, but it should be removed soon or in the future. I don't promise the time right now. Okay, so let's go to Julia and download it. Again, currently it's in the registration process. Once registered, you can just go to the package manager and say add distributed workflow, and it should download it as any other Julia package. At the moment, you have to give it the GitHub URL, and it should work. If it doesn't, please contact me. I'll see what I did wrong there. But it works. I checked it tonight and last night and in the morning. So once we have the package downloaded, now what do those 5 steps we saw earlier look like for us? Well, for distributed workflow, again, you need your Julia application. You need to know what do you want to compute in parallel. You need, based on your application, to design the PetriNet workflow. By staying in Julia, no XML code required here. There's a nice PetriNet structure, and everything will be done for you, and you would not know what's happening behind the doors. You can if you want to open up the source code. But, okay. If you are not relying on the serializer provided by Julia, you're free to use your own quirky serializer format. I tried it with JLD2, or you have some other serializer format because you might think that Julia's native serializer is not sufficient for the data types you have. We are completely serializer agnostic, so you can use it. You just have to provide it with a serializer descriptor. We will look at the example soon. You have to set up the workflow launcher, which is also done within Julia, and then you submit the job. So let's proceed. You do using distributed workflow, and hopefully you see this nice ASCII PetriNet as our welcome banner. And let's say the Hello Julia example or Hello World example I want to execute is a simple function which takes 2 inputs, 2 outputs, does something in the middle. I don't really care, it's just an example. But what I care about specifically, to know that I'm not going crazy, is to pass a sanity check which says, if you are reading this, your application worked. Celebrate. I should add that. And it would return you the output string, which is your sanity check, and your result. You don't have to pass the sanity check every time. It's just for the example. So how would the PetriNet look in this case if you want to draw it by hand? It would have 2 input places, P1 and P2, connected to 1 transition. So the transition corresponds to your function. And it has the sanity check output and your result output. And the way to write this PetriNet in Julia would be to, can I use the pointer here? Oh yeah. So you can create an empty PetriNet object, give it a name. I called it Hello Julia, so it tells you how many ports, places, transitions you have. And then you populate it by giving your places. So place, for the lack of imagination, input file 1, input file 2, output file 1, file 2. The transition, which would run your function. And how do you want to connect them? You want to connect the transition T with place 1 and 2 with the input arcs, and 3 and 4 with the output arcs. And how do you want your data to be transferred? You want the 2 places to take the input tokens and throw out the output tokens. These are connecting your workflow to the outside world from where it would access your serialized data and return you serialized data. So once you've connected, you can see that here it's populated now with 4 ports, places, and 1 transition. And you can view this before even compiling it to make sure everything is okay. You can use our view function and do something like this. This is a PNG format file, but you can also create it in any of your favorite file formats. I used GraphViz, so whatever format GraphViz allows, this can do. And if you're happy with it, you see, okay, yes, I have all the connections in the right places, I can continue with the setup of my workflow launcher because I want to use the native serializer. We can move ahead. If you're not happy with it, you made a mistake, we have a convenient remove function from which you can remove your place or arc or transition and reconnect it. You don't have to start over again. So setting up the workflow launcher, so you have to store your PetriNet either in a file, which is what I like to do. I like to place them in a script so I can locate them later, or you can do it in the REPL and compile the workflow in wherever you want. I created a temporary directory because once my application is done, I can delete all of that. And all of this is done for you once you run the compile workflow. If everything went well, you should see the success workflow compiled message. If not, you should see a error which should not be that difficult to debug, but I will add a troubleshooting page eventually to the repo. Okay, so the workflow is compiled. Now let's set up the workflow launcher. For that, we first need a client who would know how you want your execution to perform. You add the number of workers. It's a small example, so I took one worker. Where do you want your node file to be? And currently, I tested it locally because I don't want my sysadmins to be angry at me by using expensive cluster resources. So you can test it locally before acquiring resources. So you set it to local. It initiates the client. You get some message from the underlying workflow manager. And then you have to do some other. So this is where you actually create the workflow launcher. So you have to populate the input-output ports, the function name that should be executed, which it looks up in your application file, and the configuration of your application and configuration of your workflow. At the moment, you have to pass a serialized data stored in a file. So the input file here, this is also, by the way, part of the examples in our repository, where I have the initial inputs stored as the native, stored using the native serializer. And you have to pass it as a vector to your submit function. So this is pretty much all you have to do to set up the workflow launcher. And once it's done, you can go ahead and submit your workflow with the client you started and the workflow description you provided and what input variables you had. And again, hopefully everything goes well. You get one thing I forgot to mention, which is in the previous slide, you can also tell it where to store your output. So your output directory can be set by you. And it would return you the file names of your outputs. And I gave it a variable name submit func, so I don't have to write the entire string. And using serializer, you can simply deserialize the functions, the return values, and yay, success. And at this point, you're like, but you said it's serializer agnostic, and you're just showing me the example for the native serializer. So if someone noticed, I skipped on step 3, because for the native one, you don't have to describe a serializer. I forgot what I called it, but serializer descriptor, thank you. So let's have a serializer descriptor. I used Oscar because, so as I said, I tested it with JLD2. It works just like the Oscar example. However, the Oscar serializer is a special serializer, so I wanted to see if it works with that as well. And since I'm a mathematician and I'm going to use Oscar, mostly I want, again, it's the reasons this package was created was out of selfish reasons. So I tell the Julia native serializer how to save and load using Oscar, and this is the only thing that needs to be added to your application script where you have your application functions connecting to the transitions. And nothing else needs to change. Your workflow remains the same, your config remains the same. The only thing that changes now is your serialized data. Since you're now asking to be serializing it with Oscar, you have to store your input parameters with Oscar serializer somewhere on your system or a shared file system. And then if you run the submit function, it should run fine. And if you try to deserialize it using now the native serializer, yay, it worked, because it can't deserialize, because we didn't want to deserialize, and the native serializer cannot deserialize Oscar data. However, Oscar works. Oscar is reading the data that was generated. So when I saw this, I can't tell you how happy I was for the first, when this showed up on my screen for the first time. And I'm still just as surprised when I see it every time. So yeah, this is your basic Hello World example. And now I move to some of the features due to lack of time. So some of the important features of this package is ease of use. I will insist on ease of use at every part of this package. We reduce the complexity, as I don't think I need to say more about it. It is serializer agnostic, as I just proved it with the Oscar serializer. The API, the public API is completely documented, and most of the functions also have examples. I'm in process of adding examples to the ones where it's missing. You can locally test it before acquiring expensive resources. You can generate your Petri nets within Julia, visualize it in any format you like, convert your Petri net to the XML file without even writing a single line of XML. Submit your job through Julia, and if you want to log your job, you can also do that. There's an example, again, available online, which I didn't show here. You can create a logging port where the information would be transferred. And again, check out our examples to have a better idea of what's happening. Upcoming features, we will soon have notebook support for viewing workflows. This was actually done during this week, and it's fairly new. We could technically merge it, being a two-people team, but we still insist on following proper protocol and going through the proper release process. So as soon as that's done, this should be available. I'll show you an example of it. It's pretty cool soon. And you would get specialized transitions, again, to make it easier to use. More workflow examples will be following soon, or you can also look at the underlying workflow manager. There they have a whole database of different workflows they've used, but it's all in XML format, just warning you. There will be even more convenience functions coming in, not just for your workflows, but also to launch the workflow and configure your application. So even better UI and many other features that I would skip over for now. As any other package, we are also not short of limitations. Some of our limitations are coming from the underlying workflow manager, which is we currently only recommend you to run this for long-running processes. Otherwise, the overhead is too large for a smaller process. The official support for the underlying package is for Ubuntu 20 and 22. However, I manually right now test it, and at some point I'll automate the process. We provide you with, I believe, 6 different Linux distros to use it with. This is only available currently because, again, the underlying workflow manager only supports Linux distributions, and most clusters run Linux, so Mac and Windows are not supported. However, if you want to test it on Mac and support Mac and Windows, I highly recommend using containers, and you can run your favorite Linux distro there. And currently it requires a shared file system. And to summarize, it is easy to use. You can generate, view, compile workflows within Julia. It's fully documented. You can locally test stuff. Binaries are available. And for more, please go to our GitHub workflow, our GitHub page on distributed workflow. And as promised, here is the initial example. This is a Jupyter example, so you can do a show workflow, and it would show you the workflow in the notebook. And to find out more, please scan the QR code. If there are any questions, I'm happy to answer them.
Any questions?
So what are you actually compiling during that one phase? Like you said you took the XML file and it was being generating some C++ code, or what's happening there?
You mean the compilation?
Yeah, the compilation step.
Oh, wait, I can go to it, I think. This.
Yeah.
Yes, so it created, if you look at the extension, it's an XPNet file, which you never really touched or created. You did, so when you do an include hello Julia, maybe I should have shown it there. So I have a function called generate workflow. I did the name. I don't think the name changed. So currently the API is a little unstable because we are version 0. But I try not to change it too much, but I think it's called generate workflow. When you say generate workflow and pass the PetriNet structure, it would give you the XPNet file, and you just use the compile workflow and give it the XPNet file and tell it to do the C++ compilation for you.
Okay, thanks.
Yeah. There.
This PetriNet stuff looks pretty useful, maybe also on its own with the visualization. And I guess there's maybe also some, like Dagger does something similar. So might it make sense to like factor this out into a separate package that's independent of the workflow backend, just this graph representation and some operations on PetriNet and that stuff?
I would say maybe. So the main issue, well, maybe one issue that I can think on the spot is how would I call it? Because when we were trying to name this package, I came across a package called PetriNet already, but that's not really a generic PetriNet compilation. It's doing some physics and either ODEs or PDEs. So that name was taken, and if we separate it, then it might cause confusion for people who want to use the PetriNet as a generic workflow, and the ones who are coming from the physics end who want to use it specifically for those ODEs. I mean, sure, the physics people can use this, but they might be surprised by it. Yeah.
And maybe another question, if I may. Currently, you have to build the PetriNet in Julia with these connect operations and so on, right? So would it be a possibility to like have a macro or generated function that takes a chunk of Julia code, looks at assignments, and basically builds the net from that? Like taking calls as transitions and assignments as places, and then builds the nets that's implicit in the code?
So I would say I'm not sure if Julia can. So I don't know how to do that in Julia, but I can try to learn it. But we are trying to provide you with like convenience functions which have pre-built workflows. So you can say, okay, this is my function, that's the workflow, because my function matches that workflow. So you don't have to create the PetriNet.
All right, let's thank the speaker again.
And
Our next speaker is Attilio. He's a senior software architect at the TM. He will introduce us a new package in Julia today. It's about publish, subscribe, and remote procedure called middleware.
Okay, thank you. Thank you, everyone. Welcome. And my name is Attilio Donà. I'm working in the telecommunication industry, and I'm using Julia for my projects, for my enterprise project. But I wrote Rambus in my free time because I'm a Julia enthusiast. Okay. In this talk, I will make a brief introduction of a few necessary concepts to understand Rambus. Oh, excuse me. Yes. I will describe some few necessary concepts to understand Rambus. I will skim through the Rambus API. Sorry, ma non so. Allora, ok, let's try. Okay, I will describe the Rambus API, the three communication style of Rambus. I compared the Rambus with the Google gRPC frameworks, and I show you the fault-tolerant aspect that make Rambus fault-tolerant thanks to Visor, that is a Julia Task Supervisor. And finally, I will show you a couple of demo with Rambus. Why another framework for distributed application? There are several reasons. The first is that it's written in Julia and it streamlines it integrates seamlessly with Julia code. It is easy to use. It's suitable for simple to very complex distributed systems. And it offers out-of-the-box support for data frames. A system that uses Rambus is made up of components and decoupled from a broker. The components are the processes where the implementation logic resides, and these processes are generically called components because they may play different roles inside the distributed system. Client, server, publisher, subscribers, or might be an application that implements many of these roles at the same time. Broker route messages between components, and messages are encoded with Cyborg. That is an ETF specification that offers a small code size, a small message size. It also enable to integrate Julia with software with application written in other languages. Let's see an example of a published message on a topic called My Topic with a dictionary as a content. The total message size of this message is 17 bytes, for which 12 bytes are for application data, and there is a fixed size of 5 bytes as an header overhead. Let's note that the 5 bytes of the overhead, the header, remain fixed whatever entries you have in the dictionary, transported as a message content. And the Rambus layer on top of the Cyborg add only in 1 byte, in the case of a pub sub message necessary to define the type of message transported. In this case, this is a pub sub message. So I have talked about the topic in the previous slide. So let's focus for a moment on the concept of a message. Messages are classified into topics that might define their structure, semantics, and or purpose, such as alarms, parameters, environmental values, computational result, or whatever else specific domain concept you have. So in a publish-subscribe system, for example, think the topics as the logical channel that transport messages of a given type. The message also is obviously characterized by its content, that is 1, 0, 1 or more specific values. So to understand Rambus better, simply think the topic maps to the function name, and the content values of the message map to the function arguments. So if you on the publish orco cane, sorry. So on the publisher side, you can call this function if you want to publish a message. On the component that declared interest into this topic, the metric topic, for example, you have to implement this function. So let's see for a moment the high-level interface. The high-level interface is composed of a set of macros that instruments the Rambus component. For example, if you want to publish a message for the metric topic, you prefix a function call with the publish macro that publishes the message on the metric topic with 3 values, a pressure, the value, and a timestamp, for example. On the component that is interested into the metric topic, you subscribe to the metric topic, and you have to implement a metric function that expects 3 arguments: the name, the value, and the timestamp. And the same was true for example, the RPC and the exposed service, with the only difference that an exposed service return value will be returned to the client that made the RPC request. On the box on the right, there are a set of lifecycle macros that, with the exception of the shared macro, probably have self-explaining meaning. For example, the component macro declares a unique name for your component, or the unreactive macro stopped the broker from sending all messages destined to the subscribed topic, making the component unreactive. The shared macro, instead, is quite useful because it declares a shared object between all subscribed and exposed methods. And it might be useful, for example, to share an handle, for example, a connection database, a database connection handle, or to share an object that represents the global state of your component. We will see later in the demo an usage for the shared macro. So there are in Rambus 3 communication styles. One is pub-sub, publish-subscribe style. One is the request-response style, the classical RPC. And one is, I call it the conditional publish-subscribe. So the first two, the pub-sub and the RPC, are quite standard. The conditional publish subscribe is a Unix style of Rambus that is might be useful, for example, when updating all subscribed component with new status information when a remote component complete successfully a transaction to a database, for example. So the PubSub is the one-to-many communication pattern where one publisher produce a message, 0, 1 or more subscriber consume that message. The RPC, the request response pattern, is a one-to-one communication style when one client make a request and a server get back a response to the client. The conditional PubSub works as that. First, it starts with an RPC request to a server. The server, if responds successfully, the response go to the client, and the broker broadcast to all subscribed component their original request. So all the components subscribed are aware of the successful completion of a request. If the server instead returns an error, that is an exception, the broker does not broadcast the original request to anyone. Okay, let's see a brief comparison between, for example, gRPC, that is a Google solution for RPC, and Rambus. gRPC, as the name suggests, is dedicated to remote procedure call commands. So you have RPC, and also you have some advanced features like server streaming and client streaming, but it lacks publish subscribe. Rambus have both, and the combination of RPC and publish styles permits more complex pattern of communication. For example, a server streaming may be implemented with a combination of RPC and publish, for example. Or client streaming might be implemented with a publish from client side and a publish from server side. So how it works, gRPC? gRPC uses a Proto-C, that is a compiler, and a special gRPC plugin to generate code from client and server application. These stubs are then embedded into your application, and the implementation are written in the target language that you have. For example, in the box there is the hello world example of a server called greeter, only the service definition, not the implementation, that expose a method, say hello, that expect a name and return a greeting. So let's see how it worked for Julia. So for Rambus, excuse me. Rambus, it's only pure Julia code. You don't need a compiler or a schema language or whatever else. You write Julia code, or the definition obviously and the implementation, and you embed your code with some macro to make it distributed. So this is the server definition and implementation, and on the right the client for the say hello method. So quite simple, I would say. Just to cite some other aspect of Rambus without entering into the details. You can make a client-server simple architecture without decoupling broker if you want. You can set up private topics accessible only to authorized components. You can have anonymous named and authenticated components with a couple of RSA keys. Or you can make a custom broker if you want through an embedded a plugin that you where you write your logic. So one feature I'm excited to show you is the fault tolerant aspect of Rambus. When I started learning Julia a few years ago, I encountered this exception that prevent to do a controlled shutdown of the application. And it took me some time to understand how to manage this type of exception, leading to the conception of Visor. Visor is a Julia task supervisor that is heavily aspired to the Erlang supervisor model, and that permits to be fault tolerant to unexpected error faults, or for example also network exception, or whatever type of error make crash your task in an uncontrollable way, for example. So in the picture there are the tree of supervisor node that make up Rambus architecture, as we will see right now in the demo. So I will try to show you at least a couple of demo. The demo will be to demonstrate also the capacity of fast prototyping of Rambus. The demo will be in the interactive shell in the REPL. But remember that Rambus is designed to be a long-running for long-running application, not for the REPL, obviously. So. I just start the broker in this REPL, and I show you in the meantime that it starts the code for the first demo. The first demo is just oh, sorry, ma can you help with the? Non so se ho toccato qui. I touched here something.
I think your screen setup is okay, right?
Okay. Thank you. Then the first demo will be, for example, a DuckDB demo where we have an embedded DuckDB database. DuckDB is an in-process database that is not exposed to the external world, but it runs inside your application, and I will create just two API. A create that create the database reading some data from CSV file, pollution data. I have 3 files: Ancona, Athene, and Saragossa, downloaded from Kaggle. Another API to query the created table. Just make a select with a filter with the pollution element and a threshold. So let's start this application in another REPL. Okay, this is a RPC demo. Okay, so we have an in-memory database. So I will create some a table from Ancona. Here I have the database connection, then in the name of the file. Okay, if I want, I could query my table. Ancona. Let's ozone, for example, exceeding a threshold, and you get the first time of to plot. You get, for example, this data frame with the data from the station name of the Ancona that reports all the rows that for which the ozone exceed 150. Obviously, this is local to this shell. There is no accessible for external because DuckDB is not a client-server database like Postgres, MySQL, or whatever else. But let's see what we can do with Rambus. So, with Rambus, to expose a service to remote client, how it works? It works like that. So, you have a connection handle that is obviously local to this process. So you have to declare that the first argument of your callback is a shared object, is the database connection handle. And you want to expose, for example, to the world, the query API. Okay. So in another shell, let's start Julia here. Obviously, here you have not the query API, but the same thing you do here. You can make here using Rambus, first of all. So, if I want the same data frame in another data shell, this is what I desire, more or less. The database connection, it's not. It's a local concept of the other shell. So the city, the pollutant, and the threshold value. Obviously, if you do this, it doesn't work because query is not defined here. But to resolve the problem, prefix with RPC. So wait for the first time to plot time, just a few seconds. Okay, too long. Okay, the first was too long and exceeded the timeout. But now you have compiled the code and you have here the data frame from the remote DuckDB database. So you can also try a much bigger data frame. It's quite instantaneous, obviously, now. And you exposed a DuckDB in memory data frame and in process data frame to the world. Obviously, if you want to see some other demo, you can, for example, unexpose your server, your service. Now, let's try. you get an RPC method unavailable exception because you have unexposed the service, but you can re-expose again and you get again online the service. So it's quite dynamic on this respect. So let's see. Another demo interesting here, when I pass to the publish subscribe demo, is the possibility to interact with other languages, because the serialization of data frame, for example, is by Apache Arrow format. So you can you can use Python, for example. Okay, you can import the Rambus package. Here the API is pretty similar. So you can connect to the broker. And you can make the query. So here you have pandas data frames. You are happy to work in Python. I have no more time for another demo, or
we can reserve some minutes for questions, or you do the demo, but then we don't have.
No. Questions.
Questions. Okay. All right.
Sorry,
Any question from the audience?
I saw ZMQ somewhere. You use 0MQ for something?
See, yes.
Okay.
There is 3 transport protocol.
Oh, okay.
On
TCP,
the bottom layer, there is 0MQ, TCP, plain TCP, and WebSocket.
Okay. And did you benchmark? Done any performance testing?
Yes, but I'm not public result to go to show, because I was very concentrated to make a very simple interface. But the speed of the Rambus is quite interesting. But no, I did not find the time to make something, disclose something.
Very cool. Thank you.
Okay, thank you.
What other objects can you send? You can send data frames. Are there any other Julia objects?
You can send all primitive types. This is a Cyborg specification, so integer, floating point, numbers, strings, binaries, data frames, because it is use Arrow. And this is the best you can do, because you can integrate with every language. But if you stay inside only Julia application, you can transport whatever type of structure you want, because you use the tag feature of Cyborg. So you can define your struct, and you can transport whatever Julia object you want. But it's not optimized to encoding.
Okay, that's impressive.
Okay, Arrow is optimized, but not your custom Julia structure.
Thank you.
Okay, thank you. Grazie.
All right. Our next speaker is Stefan. He is a researcher in Kyoto University, specializing in mathematical biology. However, he's going to present us something very different. So this session is actually about the music. So he will give us a live coding performance using Julia.
If it works. Okay. So, okay, can everyone hear me? Yes. Yeah, so I will present something which is not my research, but something I do on the weekend or in the evening. And who was there yesterday evening? Okay, that's not good news for me because I cannot beat that guy. But we are still having some fun here with Julia. That's. It's in Julia, yes. So I have a few disclaimers. So I'm not a musician. I'm really not a musician. I'm really not a musician. I'm just a programmer, okay? Just that you know. So all of this here is about experimenting with the Julia tools and what we can do. And I will just steal from people who do this much better. For example, for me, the story started that like 4 years ago during Corona times, I was locked down in my home. And one thing I started is learning Julia, and the other thing which I started was falling in love with live music in the style how you have seen it yesterday. For example, how Andrew Sorenson is doing it. And an interesting thing is that these tools, they actually require similar conditions than Julia. So extempore, for example, is a programming language which is inspired by Lisp, but it has a just-in-time compiler and is able to do digital signal processing. So it's actually a language which, in a sense, is attempting to solve the two-language problem as well for that particular domain. And there are a lot of frameworks out there. We have seen yesterday one of those frameworks which attempt to make musicians able to use code to generate music. So I'm not going to compare it, and the goal of this is not to compete with these frameworks. The goal is here to have fun with Julia. So we can do it in Julia, and I don't know why, but let's try. Now comes the part which is very scary. Seeing if everything works. So the one part of live coding which is cool is that we can build up the music step by step. So I have somewhere here the script which I want to hopefully perform here, but our goal is to do it together in a little bit, and let's see if I can play a note. So later I will also explain a little bit how all of this works. Shall I zoom in? Yes. We don't need much of the terminal anyway. Here. So play note is a function which is calling port MIDI, and it's a small C library. We give notes like yesterday as numbers, and 60 is, for example, the C4 note. Then we can give a velocity, let's say 120, and the duration of the note. Yes, it works. So here we can hear the sound. And okay, that sound is not planned, but let's hope it goes away. So okay, now basically we can play around with this. And one interesting thing is now we can put it into a loop. But putting it in a loop, how we have seen yesterday, is a little bit boring because the loop plays once and we cannot change it. What is more interesting is, for example, the concept of temporal recursion. So I could call a function, which I call something. It doesn't really matter here. And here I could say, okay, let's play my note. And for the moment, we don't care so much about global variables, okay? So let's say this. And then we say, let's sleep for a certain duration. Let's say 1 second. And then we could call this function again, like this. I need to call the function. Okay, but now what I want to do is I want to change the function while it's running. So does someone know how to do that in Julia? What do I... Closures. Okay, I don't know if I can do it with closures. But some other suggestions? Exactly. So if I, like, while the first thing is I don't want to block my session, so I could call this here with async. And then if I put here invoke latest in front, so that's in base, but late, is that correct? Okay, that is correct. So now I can do things like okay, so this is actually how Andrew Stevenson is creating all his music by making these temporal recursion loops. But of course, we can also just make a for loop which calls with base invokers. So I have implemented that as something I call mRepeat. So this has the metronome and it eats a function. So it's a simple for loop which just calls this. And in this way, I can basically work a little bit nicer with this. So now what I'm going to do, I want to play a small melody. And this mRepeat, it assumes that I return true and some inputs like this. Let's say this is a counter and my instrument is the piano, so I get rid of this really bad global state. So now yeah. So now I can play around with this thing. And one note is one thing, but we want to maybe play a melody. So this is now a function which just eats like a few notes, and I can give some rhythm to it. Let's say just duration and some velocity. Let's say we want to randomize the velocities. So I want to have values between 40 and 80 and 4 of them. And duration is, let's say, 1 beat. So I'm now replacing that. Now we have a little bit of a melody. And for this melody, maybe we want to make it more interesting and add like something like a root note. So here I'm now copying actually a performance by Andrew Stevenson, but it's much more entertaining to have good music instead of my crappy music. So what I'm doing here now is, let's say we have a reference in a global state, which is some, I don't know, some note. I memorized the modes. So root is my reference, and now I want to play, oops. I want to do this, and everyone who knows Julia can read it. So now we have put the last two together, and we go always back to the root. And now we can do the following. These inputs are going to be the inputs for the next call of the function. So what I can do now is that I change my root node every few steps. So let's say every 2 steps I say the root is a random element, and let's say I have 50, 52, 48. And I want to take these nodes, but I want to remove basically the current root node. Is not the current root. Let's see if this works. What did I do wrong?
The function is root equals root, not root equals root index. In line 15.
Line 15.
I think root equals root.
Ah, yes, thanks. You are much better live coders than me. Thank you. So now we have a little bit of some music which is moving around. And okay, let me copy the next hand maybe, because I think it's going to be more entertaining if I don't make so many mistakes because of being nervous. When we are now generating music, we can do a lot more things. For example, we can introduce scales. Scales are basically notes like the C major scale or something like that. And here what this nice function here is doing is that when E is increasing, we sample a few time points, and then we can put these time points into a cosine function. And we can modulate with a lot of, with different frequencies. And by using this trick, we can generate basically a melody which is like going up and down a little bit unpredictably, and then we quantize it to the scale. And if I'm adding this, we can generate basically a little bit of beautiful music with a small Julia program. And all of this can go much further, so I'm just adding a little bit of drums. These are just like the MIDI notes which perform certain drums. And because of invoke lightest, we can also now change something in these functions all the time. So if I want to, I don't know, put these notes a little bit lower, I can change it while the music is playing. And this is the art of live coding. So you can now like experiment with the program and try something crazy. I'm too scared of doing that, to be honest, right now. So I will just copy one more line from here, which should introduce a nice bass to it. And then when you perform it in the end, you maybe want to pull out these elements. So one way to do that is like to make everything a bit more silent. Oh, I'm really nervous. Well, I'm usually not a nervous guy, but yeah. So let's stop it here. So this is what I wanted to show you, and now I want to present a little bit how all of this is working. So let's go back to the slides. So actually, there's not so much going on here because all we need to do is to send out MIDI notes. And how this is working is I used CLang, which is a classical tool to wrap a C library, and created this port MIDI library, which allows you to send and receive MIDI notes. And the only new part, so to say, is that I can now write this function PM write short is the function from port MIDI. And with this function, I can send a note on and note out of message. So you can see this is allowing me to play a note. And then there's a little bit of code to load basically the MIDI channel and all of this, but this is very uninteresting. If people are interested in using port MIDI, then we can of course make a nice Julia wrapper around of it, but I didn't feel like the right person to suggest how to make a MIDI library. But please chat with me if you want to use MIDI in Julia. And the setup is very simple. So if you want to replicate it, you need a Julia session which sends out MIDI notes. Then you need to create a MIDI channel on your computer. So loop MIDI is, for example, on Windows the solution for that, and there are built-ins on the other operating systems. And finally, you need something to generate the notes, which is here with sound generating. I'm just using a computer program. So just showing it here, I have loop MIDI, which receives the notes, and then I have this computer program, which has some tools basically to make the piano sound. So in this sense, there are also free alternatives. So for example, if you don't want to spend money, I can recommend a program called VCV-Rec, where you can do quite a lot of things. And now a little bit about the Julia for the timing. So doing the timing right in these kind of things is very challenging because your program is running and you're maybe interrupted by just-in-time compilation. So the game is somehow we have these notes which my program should spill out. And how do we do it? So the beginning of, let's say, we are focusing on one bar. One approach, how I solved it, probably not the best, is we can use the async function to basically execute something and directly continue the logic of our node generation. So, for example, I can use async, begin, blah, 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 to play the notes, and I can sleep in between notes. So, for example, if I want to play these 2 notes, I can say play note, sleep for 2 beats, and play another note. And this would then be a function where the execution takes, like, for example, this long. And there's a little bit space left back here. And this space here we can use to compile with invoke latest, maybe the function which has changed during the execution time. And one important thing is now for the implementation, if we use invoke latest and directly continue with play node in the function, then actually it will there will be a delay. So the smart strategy is that my function, which is spilling out the nodes, has in the beginning a sleep, which expects that it's a little bit ahead of time, and then it sleeps just until the moment when it should play the node. And because all of this is inside the function, I can compile it, start the function ahead of time, and then play the nodes. But there are much smarter strategies out there to do that. And yeah, the worst thing which could happen is that for some reason this function takes too long, and then we could get into the situation, like when the compilation takes too long, we could get into the situation that we skip over an entire beat. But at least we only hear no music for 1 beat, and then we are again in sync. So this is how I used it in this example. And now this presentation, I tried to make it short because I think it's maybe interesting to chat about what one could use with this tool. I made actually 2 other demonstrations. Maybe I can ask, who wants to hear generated drums and who wants to hear some ambient music? So who wants to hear drums? Okay, and who wants to hear ambient music? Okay, ambient music. So I will load the second session here. So now here what I prepared, and this time I'm sorry, I will just pull out the code and show it to you. So here, if I can talk a little bit more about this init session. This init session is really just a 100-line Julia file which doesn't do a lot of things. But the metronome is basically only something where I save how many beats do I want to have per minute. An instrument couples the MIDI stream, the channel, and the metronome, so that whenever I pass the instrument somewhere, it has all the information I need to play in tune. And now here with this chords function, what we can do, for example, is that we can generate random chords. So here I just have a few offsets, and I can take a random variation of these offsets, add it to my root, and maybe my root I can change it every few bars how we did it before, and then quantize it. So if I'm doing this, do we get something? So this is silent. So I need to restart the session. And here with the lead, I just used a small offset and I randomize every few iterations basically the how high these notes are. This is a bit loud. And then I created some drum pattern on top of it. Yeah, when I started learning Julia and making music with it, my goal was to generate such music and then just code a little bit more Julia endlessly. Yeah, and I think maybe that's a good point to stop here with that demonstration. I have a few more outlooks. Basically, I just talked with George, that series from the Agent JL. And he is a drummer, and I think he is quite famous for his talk he gave on drumming. And I just figured out that you can also use his package on generating motifs and hook it up with this port MIDI to use his crazy motifs he generated and play it through port MIDI. So I just copied from his webpage some crazy thing. I can quickly show you that. I need to stop these loops. So this is now a motif generated by the package music manipulations, which allows you to generate random note sequences. And I did the mistake again. Yeah, and with this I will then basically end my talk. The next steps could be, who wants to use that? Shall we make a proper package out of this? There are things which one can do, like, for example, generating actually sound with port audio and doing proper timing. And finally, one can integrate these things with musiccoe.jl or music manipulations, for example. And this is the drum pattern that was generated by music manipulations running through port MIDI. And with this, I want to close the talk and thank you all for coming and motivating me.
Do we have any questions?
Hi. I liked your talk a lot, and I have a question. Maybe I missed it. Do you have any string instruments currently programmed in your code?
So this code is only sending out MIDI notes. So the program receiving the notes could have string instruments. Yeah.
Okay.
So.
But you haven't played around with them yet?
No.
Okay.
Actually, I thought I have much more time to prepare, and I didn't.
So also answer to at least one of your questions. Yes, please make it into a package.
Thanks.
Yes, I agree.
Yeah, really cool. I've also played around with music generation that was, although not in Julia, like years ago. And I always disliked that things were so in time usually, because, I mean, right, you do 16ths, you do whatever. And have you ever thought about adding some like humanizing algorithms to this, so that your whole time base basically wanders around some tempo and it is not so static, right?
So I didn't, but George did. So he has the humanize function.
Oh.
And yeah, that works. So all I needed to do is to write this like 5 lines of codes to play the notes according to his setup, and yeah.
So I guess that's for like a given number of notes, right? And then it shifts those around, right?
So you can also humanize in these demonstrations quite easily, because so here's the duration of the notes, and these are vectors, so I can just add random elements to it.
Yeah, yeah. So I was thinking basically
that works
doing
on the
this
fly.
while your metronome is running, and then I assume there's some, or is it just a sleep, right? But
Yeah,
maybe like random, putting like a small random on the sleep, right? So that
that would directly work. So here, in this duration of the notes, or now here, one of these inputs, I think this one is the duration of the rhythm when the notes start, and this you can randomize however you like.
I don't have a question, but I have a comment. This is really cool. Thank you. This is great. Forget making a package. I want to put it in bass.
Yeah, it's only 120 lines. Thank you so much.
But yeah, actually, I think, but seriously, I think we should use this as an example in the manual for @async. I think that would be really cool.
Oh, wow. Thank you.
So 2 questions. Number 1, is the fact that Julia's sleep only has millisecond resolution a impediment here? And can you say the sentence, Jameson, I need sleep to have microsecond resolution for me, so that I can convince him to do that?
Is it a tongue twister? Okay, to answer your question, actually, the proper way to implement it is that port MIDI is a C library which has a threading based synchronization. So you have you have an input there to give a very precise offset to your notes. That would probably be how one should solve this. And I don't know if I need a better timer, but I'm sure we need a better timer.
Thank you.
Yes, so I have a question. So now you're doing MIDI output. Have you tried playing around with MIDI input as well to sort of be able to manipulate it using external controllers?
I
and
haven't
stuff?
played around with it. There's a C function callback, so it should work, but I didn't try yet.
Thanks for the demo. Once again, love these live music coding. I'm not necessarily having a question, but I do think there is a big gap where you can really make a lot of musicians, professional musicians who know scales and stuff, happy. We have, there's this thing called a looping station which does take MIDI input and then place it back in a loop, and you can use these pedals to do it. And at the moment, these are proprietary devices. So it would be amazing if you could code something like that, which takes the MIDI input and uses all this threading in Julia. You can make it open source. You can make somebody the budding musicians can use their laptop to make amazing music with this. So I think as an open source language, this would be a very nice project for anybody who is into these things.
Thank you, Jacques. I think one cool thing in general would also be there's a new plugin format called Clap, which is quite friendly. And basically merging Clap with a Julia, something which can call Julia code for digital signal processing could be quite fun in that area. So I agree, but it's a lot of work to make these things.
Obviously, I'm just throwing it out there.
I suppose this is a bit less about what you're working on and more about that music manipulations package and that humanize function. So while we were I was looking at the source real quick, and I noticed that it seems to use it adds noise, but it doesn't seem like any of the noise algorithms that are currently available to it are kind of continuous-ish. So I've heard in the past, and it makes sense to me that it would probably be most productive to add some kind of fractal noise to it. In the past, I was working on a fractal noise package for fun, but I never published it because I never finished it because I didn't have a use case. But I just searched up, and it seems like other people have made some really competent fractal noise and also similar continuous noise packages that are way more competent than anything I could ever do, of course. But I guess what I'm suggesting is, maybe talk to the person who's working on music manipulations and see if they can hook up that humanize function to one of the many fractal noise libraries we have in Julia now.
Okay, cool. We can see what happens. I will chat with him.
I think we have time for one last question.
Yeah, love this. This is great. Yeah, my question was, it seems like for live coding, Julia's syntax is getting in the way in a lot of cases. Have you thought about creating a macro to make some of these constructs easy to write?
Yeah, actually I started with macros and then I turned back to functions because one thing which I like about this Julia code, I don't know how you felt about it, maybe it's a bit fast, but it's relatively readable. So you can look, for example, at this definition of the left-hand side here. It's quantize melody, whereas where I stole it from, basically, the Lisp it's a bit harder to read, at least to my eye. There are some people who will disagree. Yeah, but you can definitely make a lot of macros and super cool specific quick language for that.
Yeah, of course.
Yeah.
I mean, this is great to read. It's just that if you're live coding,
Yeah,
the
you miss
least
a
number of
bracket and then-
characters is important.
Yeah.
Yeah, anyway.
Yeah, definitely.
Thank you.
So thank you very much, Stefan. Now, round of applause, please. Yes.
We have a 10 minutes break. All right, I guess we can start. And also people can watch online or watch the recording. So, all right. So our next speaker is Nicholas. He's currently a PhD student from University of Tübingen. And today he is going to talk about a very important topic, which is this matrix vector product using Julia package.
Yeah, exactly. Like I'm going to talk about a really important problem. More specifically, I'll be talking about diagonal estimation or implicit diagonal estimation. And yeah, but before I will go in, I would like to highlight that this is a joint product, and like to thank my collaborators, Claudio, Felix, and Elias. So this is also really international. Also, like the main collaborator, Claudio, is unfortunately not here, but he's at Harvard at the moment, and we're like closely collaborating on this. And yeah, what will I be talking about? So as I already mentioned, it will be about implicit diagonal estimation, or the randomized version of this. So we'll go into what is this, why do we need it, and what does the Julia package what can it be used for, what is it about? So yeah, let's get straight to it. What is implicit diagonal estimation? So implicit diagonal estimation refers to the fact that we have implicit access to a matrix or a linear operator, in the sense that we do not have access to the exact entries, but we can access its action, or a so-called oracle, which means we throw a vector at it and then we get a times x back. And our goal is to estimate the diagonal. I mean, in the sense, this is a trivial problem, because you can take the unit vectors and then you take n unit vectors and you can extract the diagonal exactly. But this is kind of suboptimal for large matrices, so we want to get good and quick estimates. And yeah, this is actually not a super new problem. So there's an estimator for this called the Girard-Hutchinson estimator, or sometimes also BKS estimator. And it's pretty much influenced by the related trace estimator. So if some of you have seen that. But the difference is that for the estimator, we're taking point-wise operations, in the sense that we have Hadamard products here in point-wise divisions. And yeah, we do not need explicit access to the matrix, but only implicit access. And yeah, a few comments. So what are these V vectors? These are random vectors. That's also where the name randomized diagonal estimation comes from. So these are isotropic, and it can be Rademacher, Gaussian, whatever. And this estimator is unbiased, in the sense that it in expectation estimates the diagonal. And therefore, it's a prime example from this field, randomized numerical linear algebra, which is like upcoming and actually supposed to kind of be a fill-in for the like old numerical linear algebra, and it's really like a hot topic, so to say. And yeah, so this is a really well-formulated problem. It's there's, so to speak, a solution for it, but like, where do we need it? Why is this of interest? And yeah, I collected 4 examples for this. The first one is from network science, that we are interested in calculating like centralities, which are given as diagonal entries of exponential of the Grasp-Laplacian. Then in material science, there are some like charge densities, which are kind of diagonal entries of this density matrix. Then in optimization, there's an optimizer which uses diagonal entries of the negative powers of the Hessian matrix, and uncertainty quantification, in particular for regression problems. These the diagonal entries of like this Gram matrix basically give you uncertainties for coefficients. Yeah? These are all like examples where we want to calculate diagonal entries of matrices that we do not have explicitly. And why do we not have them explicitly? Because it's all functions. Yeah? This is also a core aspect of this package, that is able to calculate the diagonal entries of matrix functions. Yeah? And for matrix functions, we do not calculate them explicitly because it's very expensive. And so like 2 slides ago, I presented the like generic estimator for randomized diagonal estimation, but it has like one kind of flaw, and that is that it's relatively slow. Yeah? So you need many entries to get a good relative error. So there have been like substantial efforts to speed up this estimator and get improvements. So what are the kind of state-of-the-art methods that we would use to tackle this problem? And there are two main improvements over the standard Julia-Hutchinson estimator. The first approach is so-called deflation, and that is we do not use the diagonal estimator on its own, but we use it in collaboration with a low-rank approximation. That is, we approximate the diagonal through a low-rank approximation, a randomized low-rank approximation. That gives us already an approximation of the diagonal, and then we use like the remainder of the matrix, meaning like matrix minus low-rank approximation, and approximate the diagonal of that matrix. And that already improves very much for like approximately low-rank matrices. The second type of improvements are the so-called adaptive algorithms, and they tackle the question like of the number of test vectors that we need, because it's a priori not clear. And the main like improvement that we present is the extension to matrix functions, in the sense that we can now calculate the diagonal for not only matrices but also matrix functions, and that we use through combining the Julia-Hutchinson estimator with approximation schemes for matrix vector products for matrix functions. And there we particularly look at two types, namely explicit polynomial approximations and these Krylov approximations. Yeah. And this is like all these state-of-the-art functionalities basically condensed in the Julia package. So we have two functions that we export in the package, and that is like estimate diagonal, which is the standard diagonal estimator, which takes a matrix A, a stopping criterion, so either you have like an explicit number of test vectors that you want to use, or you say I want to stop adaptively with like adaptive criteria, and also distribution. You can use any distribution basically. And the second function, which is kind of our main contribution, is the extension to matrix functions. So you can insert a matrix and a function, so you don't have to know the exact value of the matrix function, so you only insert the matrix itself, and then specify an approximation scheme for matrix vector products with the function, and this then kind of specifies the algorithm that we implement. And to give you some insights and some brief results, so I cannot go into detail here obviously, but to give you some kind of pointers on which method do I use in which case, I prepared 4 like examples. And so the main decisive factor for which algorithm should I use in which case is the spectrum of the matrix. And therefore, let's look at these 4 different example matrices. The first one has like a flat spectrum, so linear interpolation. Second one has a step, so a certain number of eigenvalues are constant, while the other ones are like smaller, also constant. Then a polynomial and an exponential spectrum. So these are the eigenvalues, and then we like compute a random matrix out of this, which are now our test matrices. And now the point that I want to make, the spectrum is an important kind of influence for which algorithm we want to use. So we can calculate all of the diagonals for these matrices and matrix functions. So here I plot the logarithm of matrix plus identity matrix, and the point is for flat spectra it's best to use the canonical estimator, while for the matrices which have like steep spectra, that's better to use these low rank approximations. So this is kind of the takeaway, which I also formulated here in the box. And yeah, basically to conclude, what are some outlooks that we want to improve in? So we currently summarize the state of the art in terms of methods, but there are some implementational aspects that we would like to improve on. The first part is that these methods are easily parallelizable. So this is what we want to look into, to really speed up and take the best of like hardware requirements and stuff, and also add further Krylov approximation methods, and dedicate these also to special matrices where we know that the estimator is kind of not performing well. So there's been a recent publication on this issue that for certain types of matrices it's kind of slow. And the next part are matrix-free implementations. So for now I have to give the algorithm a dedicated matrix, but this also works for general linear operators, which is like an extension. And also feedback from the community is very welcome. So in case you would like to have a look at our preprint, which is coming soon, so there's a website where you will then see it, or the docs, or also my thesis I wrote about it. Feel free to check out these websites. And by that, I think I'm at the end of my time.
Yeah, thank you very much.
Thanks.
Perhaps just one quick question, if there's any. If not, I have a question. How does this scale? So for example, have you tested, let's say, 10,000 by 10,000, and how quick does it run?
I mean, the decisive factor is this matrix vector product, and this is the scaling part, yeah. So the number of test samples you can select your size. So it's linear in the number of test samples, which is kind of the only aspect that's
okay, so you expect,
it
for
scales
example,
as the matrix vector product.
Okay, so it's a scale linearly.
Yeah.
Okay, all right, thank you.
All right.
All right, so our next speaker is Ludwig. He's from, no, it's you. Oh, okay, sorry. You're, okay, sorry. Right, sorry. Oh, it should be, okay, should be okay. And then you want to have this, do you have the USB? Doesn't, then you can use this port. Okay. And then you can use this too.
Okay.
All right, so our next speaker is Samuel, and he's going to talk about sustainable development. Thank you.
All right. Welcome everyone to my talk on sustainable development of stencil-based HPC applications. So I'm Sam from CSCS, ETH Zurich, and here are my co-authors. In HPC, the challenge that we have is the same since a while and will be for a while, right? Scalable performance, performance portability, productivity. Basically the main response to this challenge from us is to do automatic shared and distributed memory parallelization and optimization of architecture agnostic code. And to do that, we create HPC building blocks because I strongly believe that the challenge needs to be split up into manageable tasks, where the demanding computer science tasks are then largely solved in such building blocks. And our building blocks are instantiated in these packages. I will give you, in my talk, a quick overview of these packages, and then afterwards explain our approach, meaning also these packages on code examples, and then give results and conclusions. Overview of this building blocks. Well, first, we have certain requirements that come from our projects, right? Here, this GPU4Geo project. A big amount of requirements. So they're always, it's different to just do something without thinking about the real world applications, or then really try to do it in a way that it can be used in practice. in general, Parallel Stencil and the other packages, what they do, Parallel Stencil is hardware agnostic. It allows to write hardware agnostic kernels in mass close notation or explicit, and automatically optimize it, optimize code, stencil-like or other code. And stencil-like here is really the widest possible sense, basically relative indexing with respect to a thread ID. Implicit global grid is distributed parallelization, and cell arrays for GPU-optimized logical arrays of arrays of structs. Now, what is new? Or more newish, let's say, we have AMD GPU support for all of this. And now in Parallel Stencil, we have code generation of polyester code in order to multi-thread, which is in particular efficient for small problems. And also we fully use and embrace the Julia extension feature. So I quickly show you here how that it could look like. So we have first CUDA extensions, the module, right, when you create an extension, an AMD GPU extension and the package. And each would just initialize Parallel Stencil with the corresponding backend. And then what's particularly, then the code that we would include here can be shared. It doesn't have to be different. And Parallel Stencil generates, in the end, just regular CUDA code or any GPU code. And so, of course, to create an extension is just the usual way, right? And yeah, just remember or think that init Parallel Stencil is to be called just each time in each module after using Parallel Stencil. So it basically gives you the flavor of the module. Now, to give you an explanation of the approach in this code examples, we have a very high-level way of writing things, very mass close. You see here Fourier's law of heat conduction, conservation of energy, update of temperature, really nearly written as you would write equations. And what is particularly important to see here, the fluxes and dt is not stored in memory, because you see in the signature of the function it doesn't appear. So it will automatically be done on the fly. Also, one can use other macros. You can define them yourself, right? Then that was the kernel, right? And in addition to that, of course, we need to have some allocation of arrays and then call our kernels, and that's what we see here. And what we have in particular here is we have this feature hide communication in order to overlap the computation with the communication. And so what happens in general is we compute the boundary regions and inner points on different streams. And as soon as the boundary region is finished, we start the Halo update. And then, of course, that is runnable on a single CPU core or on thousands of GPUs. Now I will just do a quick dive into the hiding of communication, how that looks like. So if things go wrong, if you, for example, here put a synchronization after each call, then you will have these gaps here and nothing overlaps. And you can see here, just to understand what's going on here, in blue there, in the Halo communication part, you see what is written into GPU buffers, and the like brownish part is actually the transfer from CPU from the GPU buffers to the CPU, and through the network. Then this is all done by the GPUware MPI. And so the network communication is not visible, but would also be there. I see that the time seems to be up. I only have 7 minutes on my chronometer, so I need to go a little bit further. Sorry. Then you see here, if things go right now, how it goes. We have boundary region computations on the left, and then the overlap of the inner point computation with the halo computations. And nice to see here is that the boundary region computation, if you zoom in, they also overlap partly. And actually that means that when the kernel has not anymore enough blocks to saturate the GPU, then the next kernel already starts and can that way saturate the GPU at all time. Now this here would show how it works when we don't have GPU-aware MPI available. And so what's nice to see here is that it basically looks the same way. You see these little blocks are about the same size as before. And there we also have these brown things there. And one is highlighted in yellow. And this, if you look at the bottom right, you see we have a throughput of 2.9 gigabyte per second, which is basically the peak performance of the PCI Express that we have on PitStained. And so the result is we get a similar performance as with GPU-aware MPI. Now we can also, when we have multiple arrays, we can overlap these different arrays in the data transfers. And I will try to speed up now very much, so we can do many more things which we have talked about already in the past, like automatic differentiation, etc. We have also logic arrays of arrays, which I've only mentioned. I will not go further in detail now. And we have a magic flag to do memory optimization. And this, the results of that I have shown already in last year's talk. Check that out. Scalable 3D PD solvers tackling hardware limits. So there we could show that we really get very close to the peak and get a significant speed up over explicit CUDA or KA. Then we have some quick scaling results here. It's like 93% for diffusion and 96 for real-world applications. Here we have on Lumi the diffusion, and here a real-world application about 96%. That is all. Thank you very much.
Thank you. Very nice result. Actually, I also used PitStained at some point. So yeah, it's very nice to see that there's a continual improvement on performance. All right. Any quick question? If not, I just want to ask a very brief one. What's the geological application you're trying to solve?
One of them is ice sheet flow, which has been presented in other talks, with fast ice, etc.
Okay. All right. Thank you. All right. Then our next speaker. Yes. You both present? Okay. Okay, so our actually next two speaker is Sebastian and Sathvik. They're from GitHub. And JuliaHub, sorry. JuliaHub. Oh. And okay, I also use GitHub. All right.
Hello. I will be talking about robust calibration with Julia Model Optimizer. So first, what is JuliaC Model Optimizer? JuliaC Model Optimizer is a product from Julia Hub for parameter estimation and in general optimizing models to match data. And I will now go a bit into the problem that we're solving here. So for parameter estimation, we usually have, we build complex models to describe real-world phenomena or real-world applications. And in order to have the models match reality, we usually rely on calibrating the models to data that we have collected. This process is not always very simple because for complex models you might have situations where it's not easy to feed the real-world data or the data that was acquired. And this comes from the fact that when we have complex models or very high-dimensional search space, the loss that one would use can be very complicated, like in this example. As we can see, there are a lot of local minima in here, and using optimizers can lead to getting stuck in such a local minima. For example, if we were to start in the blue point here, we can see that we have several possible scenarios of what a local optimizer might choose as the path to the solution, and we can see that it can get stuck in a local minima. What we would actually want is to be able to traverse these local minimas and get to the global minima. So what can we do about this problem? So what are our ways in which we can prevent local minima? One of them is, instead of trying to fit an entire trajectory at once, we can split the trajectory in multiple segments. So we'll have smaller trajectories that we need to fit, and the starting points of those small trajectories will have to be determined by the optimizer. Of course, now that we split the problem in several subproblems, we need to make sure that the problem that we are solving is actually corresponds to having one trajectory. And this essentially means that we have to ensure continuity. We can ensure continuity either via constraints in the optimizer or via a penalty function. And as we can see here in an example, we have the segments here, and here we are enforcing the continuity via penalty, and at the same time we also have the cost of the difference to the data, and they are simultaneously optimized. And we can see as the optimization advances in the number of iterations, the segments tend to get closer and closer, and then they form a continuous solution, which then we can see that it also fits the data well, avoiding the problem of local minima.
Okay, so along with multiple shooting, we can have a prediction error method, which basically mixes data with the solution, and you can sort of nudge the current simulation towards the data. So mathematically, it's a ODE transform, which results in a very smooth, which smoothens the loss landscape. So this loss landscape you see on the left is actually a prediction error method smoothened loss landscape of the one which we saw in the first slide, second slide. So you can see that that loss landscape had so many minimas, but this loss landscape is so smooth that if you start at any point, it will eventually roll down to the actual solution. So this becomes important in complex systems where you have a lot of minima, and for complex models, you will have a lot of minima in higher dimensions, and this method can be used to sort of smoothen the loss landscape, which will eventually help in better calibration. So this is a slide where, so the left side basically is the optimization trajectory without a prediction error method. You can see it's sort of stuck in the valley and sort of just stays in the valley and never goes to the actual solution. But while with prediction error method, it basically rolls down as easy as that to the actual solution. Okay. So before going into code on how to use JuliaSim Model Optimizer, I just want to give a quick demo of a JuliaSim Model Optimizer in action in JuliaSim. JuliaSim is a GUI, which is a product by JuliaHub, and where you can drag and drop components to build models, and you can also have simple and optimization analysis with it. I'll just give a quick demo of it. So you can see you can select all the components to build your model, and then you can use these components to actually build the model. But in this case, we have a pre-built model for demonstration. After you build the model, you can click on the analysis tab. I'll just take some time to explain what is this. This analysis is basically like a graphical user interface for Model Optimizer, where you can select what method you want and like what is the maximum number of iterations, what optimizer, and what type of loss function. And also you can specify any data set. So this is like sort of compatible with JuliaHub.dataset, where you can upload it separately. So you don't have to upload it here. You can just mention the name and some specifications of it, like independent variable, dependent variable. Then you can mention what parameters you want to optimize and what are their bounds. Oh, sorry, what happened? Okay. Huh. Sorry. Okay. After that, you can click on simulation, which actually runs this optimization in the background. So it's in the cloud, so you don't have to worry about closing your laptop or something. Then you can come back, and then you can just plot the results and also the values of the calibrated parameters, as easy as that. Okay. So this was a quick demonstration. Now let's use Model Optimizer with some complex models. So for that, we are using it with JuliaSim HVAC. So JuliaSim HVAC is a proprietary HVAC library built by JuliaHub. So there was a talk on JuliaSim HVAC like a couple of days ago, so I won't go into much details of that. So it's basically a library of components where you can plug and play to build HVAC models. For our demonstration purposes, we use a vapor compression cycle, which is a standard air conditioning cycle, which has a condenser, a compressor, an evaporator, and expansion valve. So let's do some interesting calibration with it.
Okay, so as we mentioned before, we have the vapor compression cycle, and what we're interested in is finding some coefficients that would represent a correlation between pressure drop and blast flow rate in a pipe in the evaporator and the condenser. And why we're interested in these parameters is because they are not easily directly measured. So in order to calibrate our HVAC model, we need these parameters, and we also have we might have experimental data collected from what is easy to measure from the actual HVAC system that we have, that we might want to improve or want to study further. So let me go a bit through the API here. So JuliaSim Model Optimizer works with models based on modeling toolkits, so it's built and integrated with the SciML ecosystem. So here we start by getting an MTK model. In this case, it's an HVAC model, but it works with other MTK models. Then we define an experiment. So this is an instance for which we have experimental data. And the data can be any tabular data that we have, which has time series data for things that can be computed from the model. So predictions of the models or measurements from the model of any sort. We have a time span for the simulation, and then we can have integrators from ordinary DFQ, all the 300 plus integrators, and also all of their configurations, so anything that you would normally specify with differential equations.jl or ordinary DFQ. And in this case, we're showing the PAM part, the prediction error method. So as was mentioned earlier, prediction error method is a model transformation. So it transforms the model that you have such that it adjusts it to the data. So the predictions of the model during the simulations are adjusted towards the data. And then we have to specify how are we going to compare the predictions from the transformed model to the data. And all of this information is encapsulated in this structure that we call experiment. So if you have multiple instances in which you might have collected data, so you have data for one particular experiment that you performed and another one, and you want to use both of them to calibrate the model to fit both scenarios, you can define however many experiments that you need. Then the next thing to define is the parameters to calibrate. So this is what we call the search space here. And simply it's just the symbolic representation from the modeling toolkit model. So the interface is purely symbolic. You don't need to worry about like indices or things like that, just like with modeling toolkit. Now, another thing that we need to specify is what are the lower and upper bounds and potentially the initial guess. If you don't specify the initial guess, you can deduce that from the defaults that are provided in the MTK model. Now, what we define is the inverse problem. So the inverse problem is the problem of finding what parameters of the model that are in the search space would correspond to a particular behavior of the model. This can be encoded by the loss function to how to match the data as closely as possible. The next step then is to define a calibration algorithm. And here we have support for several calibration algorithms such as single shooting and multiple shooting, and also so multiple shooting has also several configurations. We also support the collocation methods, and now I'm going to mostly talk about multiple shooting. So multiple shooting needs the number of trajectories. So this is in how many segments are we going to split the entire time span that we have data for and we are simulating for. Then we can provide the stopping conditions, so maximum time or maximum number of iterations. So this runs automatically. So usually you want to ensure that, okay, I know that this will stop at some point no matter what, so you can check the results at that point, and if it's not enough, you can continue again. Of course, if the optimizer decides that the convergence criteria was found, then you will stop at that. But just to be sure, you can provide the maximum time. Yeah, I'm not willing to spend more than this amount of time running this. And then the next point is initialization. So this is how each of the segments, so as we can see, we have several segments for the trajectory, and we need a way to give the initial value for the segment. Since the optimizer will continue changing these values, it needs, depending on the optimizer, it might need an initial starting point. So in this case, we are using the data for initialization because the data can, in general, can be very helpful in providing us with a good hint of where the segment points might be. Of course, there might be other ways that might suit better in other scenarios. So we support several initialization methods for the segments. And next is how we want to parallelize. So we support, since multiple shooting essentially computes each of the segments in parallel, there is, I mean, this is a method that is very easy to parallelize since the individual segments don't depend on each other. Then we can use multi-threading to parallelize them, or you can use distributed, or all the options that are supported in SciML. So we are compatible with that. And then how we enforce the continuity between segments. Again, you can use constraints, or you can use a penalty. And the last point is doing the actual calibration. Now, looking at the results here, we compared the single shooting method with multiple shooting with PEM. What does this mean is that we have the, as I mentioned earlier, you have the multiple shooting combined with prediction error method. Since prediction error method in itself is not a calibration method, you can combine it with either single shooting or with multiple shooting. In this case, we used simulated data with noise, as you might have seen on the previous slide. So here, the data has noise, so that we can also check, like since we know the ground truth, we can evaluate how well does method do compared to that. So we evaluated here single shooting and multiple shooting with prediction error method. And in this case, we have slightly better results for the multiple shooting with prediction error method. For the HVAC case that we're looking at here, this is how the loss surface looks like. We have some local minima that are in one region of the parameter space. But in this particular case, the optimizer is pretty good at dealing with that. So we get a slightly better result with multiple shooting, but we don't expect in this particular case like a huge improvement because it wasn't such a drastic case as the one that we showed in the initial slides where single shooting would completely fail. Of course, this is just 2 parameters so that we can also have plots and visualization for it. If we were to have tens of parameters, then there would be no way to visualize that. But when the dimension increases, it's much likely to have, in a high dimension, to have these complex geometries where it would be much more hard for an optimization method to find the actual global minima. I think I went a bit fast, so if you have any questions, I think there's more time for that. But yeah, thank you for listening. And these are some QR codes. You can see our documentation if you're interested in trying this out. And I think that would be the end of our presentation. Thank you very much.
Thank you. Right, so in my line of work, what it is typically the case is that I have a, let's say, 5-dimensional system, 5 OTEs, but my experimental data is only 2 of them.
Yeah.
How do you, and the thing I'm interested in is how you handle the initial conditions for the unknown or the variables that are unobserved. particularly in the multiple shooting method, because, okay, maybe me as the user or the scientist, maybe I can cook up or I can smoke up an initial condition for the very start of the simulation. But now if you do multiple shooting, you have to somehow generate out of a magic hat initial conditions for the later stages of the simulation. How would this work, and even is it even possible?
So for the initial starting points, there are cases where if the observed that you have data for, if they are linear in the things that you have data for, then you can actually solve that and invert those. So there are cases in which you can invert that relation, and then you can find, so for example, if you have data for A and there is something that's an invertible function of that you have data for, then if that function can be inverted, we can do that inversion automatically.
No, I wasn't clear. I'm sorry. I have dimensions x, y, z of my dynamical system. I only have data for x and y. I don't have data for z. There is no function that can give you z from x and y.
Okay, okay.
So how would you initialize the initial conditions in the multiple shooting when the variable z has no data from you to infer a possible initial condition from?
In that case, I don't think you can compute that, but you can try strategies like if you do random initialization within an interval, or because you have a bounded interval that you're searching z in. And you can do a random initialization and do this several times and see how that behaves.
Yeah, okay. Yeah.
Any other questions? Then I think we have a shorter break. Let's give another round of applause for our presenters.
just do one more time?
All right, let's start our next session. Our speaker is Elmuji. He's a PhD student at computer science in University KU Leuven. And he will tell us how to use Julia to build a quantum state solver.
Thank you. Good afternoon, everyone. I'm working on the quantized system solver.jl, which is a package developed as a solver for another tool that is being developed in the Belgian Royal Military Academy. So to do that, I'll start by an introduction, then I'll explain what this QSS solver is and why should we use it, and then talk a little bit about the software and the improvements of this method. So introduction is, let's say that you came up with a great idea that you want to test in one of these complicated systems. Then obviously you cannot test it directly because it can be costly in terms of time and money, as well as dangerous. So we all know that simulation is the answer to this problem. But there is already many tools out there. But there is the need always to invent a new tool depending on the special needs. So as I said, in the Royal Military Academy, there is a tool called JIFSO. It's a Julia Interoperable Framework for Simulation and Optimization. And there is the need to have a solver that works underneath this tool. And that solver is the QSS solver. So QSS is basically a set of explicit and implicit methods that solve differential equations with events. So the special thing is the events. So to compare it to the classical integration methods, the QSS at a step will update only one variable, while, as we know, in the classic methods, at each step all variables get updated. And there is a new variable that shadows this variable x, and we call that variable q. So that's the added thing for this QSS method, is this q value, which is, depending on the method explicit, then will be the old value of x. If we're using the implicit method of QSS, then q will be the future value of x. To explain it a little bit more, I have this example. Let's say we have a system of two differential equations. Step one, for the classic methods, both variables x1 and x2 will get updated. For the QSS, let's say only variable 1 needs an update because variable 2 is slow and we don't need to update it. So for the explicit, we know we have q is the old value of x. So at this point, we have set q as the old value of x, while in the implicit, we set q as a future value of x. So the algorithm, in simple words, will look for what variable needs an update, and then we'll update that variable. Do I have a pointer, or does this work as a pointer? Okay. So, and then I update this variable and update its quantized variable, and then see if other variables depend on this variable, and I only update those, and see if there are any events that depend on this variable xi, and then I check if those events need or the zero crossing for those events need to be checked. So besides this variable Q, I also have a set of dependencies matrices that are built up front that I will use to check which variables need an update. Then, besides the QSS from the beginning, we see that it has cheaper steps. Also, the implicit method has a huge advantage. So we know that in the classic methods, if we have an implicit algorithm, then we have this unknown x, which is a vector, since we need to update all the variables. And if we want to look or find this x, then the math will lead us to a matrix inversion in the size of the system. While in QSS, since we don't need to update all variables at the same time, so x is just a scalar. And then the same equation will lead us to just a normal expression. So that's a huge advantage in the implicit case. Just to note or to mention that sometimes in QSS we need to update two variables at the same time. And in that case, we have a 2x2 matrix, so it's not costly in that case. So that's a huge advantage for QSS. The next advantage is the discontinuity. So if we have a discontinuity right here in the classic methods, at each step, we'll check is this function crossed 0 or not. While for QSS, since we have the dependency matrix, so if let's say variable xk changed, and we know that xk does not affect the zero crossing function, then we don't have to check for that if the event is going to happen or not. That's also a huge advantage. In addition, that we know in classic methods, we know that if the method encounters an event and then will stop and reinitiate the new initial conditions and so on. Besides that, in classic integration methods tend to decrease the step size when they encounter any discontinuity. Last thing is that in 2014, Fernandez and Kaufman wrote a paper about QSS using the C language, and they compared some of the systems, and they showed that QSS or this LI QSS means the linearly implicit, the implicit version, is way faster than Ranjakota or Dassel. So to conclude, that QSS has some advantages or many advantages in some systems compared to classic methods. So the quantized system solver architecture goes like this. So the user will have to ask to the solver to create a problem. Then that problem will be created using a problem type which has some field variables, which I will show later. Then once that problem is created, then the solve function, which is pretty much, if you're familiar with the differential equation, that DGL, I tried to keep the same interface as their interface. That solve function will dispatch on one of the QSS algorithms, explicit or implicit or modified or whatever algorithm. If you want to extend this solver, you can just create a new algorithm and make it dispatch using the solve function. These algorithms are the functions that will start the integration method. And they will use other helper functions depending on the order of the solver. At the end, the solver will spit out the solution. Again, I try to keep the same interface as the differential equation.gr. So this is an example of how we can use this solver. You just have a set of parameters. Then if you have any discrete variables, any continuous variables. In this case, we have a system of 2 continuous variables with 5 discrete variables. And this model is the electronic buck converter. So the differential equations are the current in the inductor and the voltage in the capacitor. So you do the math and you get the equations. And then if you have any events, since here we have a switching component, then you do the events for that component. And then pretty much you do the solve function on that returned problem using one of the algorithms. In this solver, we have the QSS, the explicit order 1 and 2, and we have the implicit normal implicit order 1 and 2, and we have a modified linearly implicit QSS 1 and 2, so up to order 2. And you do the absolute and the relative tolerance, and then you pretty much can do anything with the solution, query for values of some variables. You can plot the solution. You can ask for the error if you have a reference solution. And this package, you can find it on GitHub, and the documentation. It's pretty much complete. Yeah, you can see it. This is another example. Let's say this is the bouncing ball, and you can run, if you have a model that you want to run many times, you can pass the parameters, and then you can run it many times. Another thing that I wanted to show is that you can write your equations in a for loop if you have many equations that are similar. This is like the advection diffusion reaction model, which is a result of EPDE discretization. So the result will be similar differential equations. So you can just write them in a for loop. Next is the structure or the internals of these functions. Once the user asks for a problem to be created, we have a function that will decide which kind of problem is this. Do we have a problem with discontinuities? Do you have a normal problem? Based on that, then another function will be called to create the dependencies that I talked about in the beginning. So we need to have a Jacobian. We need to have some dependency functions and matrices that will be built up front. One thing I need to mention is that the variables that I'm using during the simulation are Taylor variables. I chose Taylor variables since to approximate some complex functions, so the math will be easier for the solver. And I realized after doing that Taylor variables allocate at each operation. So I added up front another function that will take any operation and change the AST to another personalized AST. So for example, if I have in the differential equation variable 1 plus variable 2, then that will be changed at compile time to another personalized function. So this function will not allocate since the output will be in the cache, it will be cached all the time. And here is the problem definition, and this can be extended from the super class that I have. So for example, if someone else wants to solve a different kind of problem using QSS, they can create their own struct. So to explain a little bit more of this problem creation, let's say we have this model, and these are the differential equations. Then they will be changed at compile time to these equations. So as a user of the solver, you don't need to know about this, but I just wanted to explain what's going on under the hood. So if you see like here for K from 2 to 999, it's here. You just keep the same format, but you just change this function or these operations to personalized functions. Also, the Jacobian of this system is or built or extracted at compile time in a personalized function. Next, once you have your problem, you call the solve function, which will create the data needed for the QSS method, and then will integrate that method with the problem in another function. So this is the struct Taylor that I talked about, that I used initially from the Taylor series.jl package, and then I created my own internally, so that all my operations won't allocate. The integrate function is the core of the solver. This is the integrate the QSS integration method. So basically, as I said in the beginning, that you find which variable that you need to update, and then you update that variable with its quantized variable, and you go through any dependencies matrices, the ST, SZ, basically which variable affects which derivative, which variable affects which zero crossing function, which event affects which variable. All those interactions between events and derivatives and variables are stored upfront in matrices. So at each update, we check those matrices, which variable needs an update, which event needs to be checked. And then you will have a solution at the end, which contains the saved times, saved variables, and any stats that you want. And also this can be extended if you want to use the solver in a different way. You don't have to change many of the functions. You can only change if you want a new problem, you just create a new problem. If you want a new QSS algorithm, you just add one here. And if you want your solution to be different, you just create a new subclass of the solution superclass. And this is a good thing, so that the solver can be extended as we go. Design considerations and dependencies. In this package, I used other packages such as Express Tool to to group all the differential equations into only one function, the personalized function that I showed. Also, I used macro tools to parse the user code, looking for any errors, and to change also the function. Sim engine is to get the Jacobian as expressions up front, and I used the at runtime generated function to avoid world age issues. The solve function uses the value type to specialize on the order and solver type. The Julia dynamic type system also used to construct different containers at compile time. I respected type stability throughout the whole solver, and as I said, the solver is designed in a way that it can be easily extended. After talking about the solver and the QSS method, I actually found some limitations in the QSS theory itself. So in the previous version, so I didn't come up with the QSS. It's the method existed before, but I improved the method in 3 ways. First, the improvement is the linear approximation. They used to calculate the Jacobian entries in a manual way. So they will, as the simulation runs, they will update the entries using the old values of the derivatives. And I realized that this method, while this entry of the Jacobian is correct right here, but after a step, or the next step, this entry can be invalid. So what I did is, as I said, I extracted the Jacobian at the begin up front, and then I will use the entries using a function, not manually. Another change that I made is that the way they compute the quantized state at each time, they use iteration. Since this is the function that updates the quantized variable, and we see that Q appears in the right hand side, and also H is unknown, the future step size, and they used iterations to find Q and H at the same time. What I did is I put a Q on the left hand side, and I found that finding Q and H can be done using functional analysis by investigating all kinds or all possibilities that this function will look like. The third and the final improvement I made is that this QSS method, while it's cheap, but sometimes these cheap single updates of variables can lead to cycles, which is bad, since cycles are unnecessary steps. So the initial way of terminating those cycles is that they try to calculate the future prediction of the derivative and see if that derivative is changing a lot compared to the initial or the current derivative. And I realized that sometimes, like the picture right here, the derivative and the future derivative can be almost equal while we have cycles. So I came up with a fictional prediction, and I used this derivative instead of the current derivative. With these 3 modifications, I tested the advection diffusion reaction with 1,000 variables, and the modifications helped to improve the solver by a factor of almost like 20, and also improved the error. As a conclusion, if you have a system of differential equations, then you can forget anything I said. You don't need QSS. If you have a large sparse system, meaning that you don't need to update all the variables at the same time, and you have discontinuities, events, then you can start considering QSS. Finally, if the system is stiff, of course, you need to use the implicit version of QSS. Thank you.
Do you have any questions?
Yeah, I have a couple of questions. My first question is, do you have comparisons with the standard differential equation, let's say benchmarks, so with this ADR system? So, because you can also do these simulations with the standard differential equation solver, right?
Good question, thank you. I did some comparisons with differential equations.gl and also with the QSS in C. I just didn't put them in here since honestly this version of my QSS is not well developed, so the results, my solver is not better than the differential equation.gl in many systems and also in C. However, in C is the solver in C is not better by a lot. It's only like 1 point something. It's like very close. Differential equation.gl, the only thing I noticed here in this example, the back converter, actually this plot is from differential equation.gl and it is not correct. So their way of dealing with discrete events is still, or they need some, I mean, I guess it's a bug maybe, I think. And I opened an issue on their website about this, and there has been some.
I guess it just misses one of the zero crossings if you decrease the maximum step size. I guess it's just that the solver of differential equations misses a zero crossing. If you decrease the maximum step size, I guess you will get the correct result.
Tried all, I just put like the minimum is like 10 to negative 12.
Not the minimum, the maximum. Because I guess he steps over a zero crossing and doesn't recognize it. It's a zero crossing that it gets activated and deactivated, and the solver just steps over it.
Do I increase or decrease the step size?
Decrease the maximum.
The maximum of?
The maximum step size of the solver, because then you force him to step into
I played with the absolute tolerance, both, and relative, and also they have the DT minimum.
Yeah, but the tolerance won't fix it, because...
I know, I'm just saying that I tried and tried the automatic without not putting anything. They have some options that I just
it's DT max is...
yeah, I tried that and it didn't help. And I think even Chris tried it and it's I think it's a bug.
Okay. Okay.
Do you require special sparsity patterns in your systems, or is it just okay if it's somehow sparse?
I guess if you have a system that you consider sparse, you can try QSS, and if it helps, then maybe but I have not played or investigated the limit on what to consider the system is sparse and should be, and QSS should be used. But I guess from the theory, you know that if some of your update variables are not going to be updated, then QSS is
What I mean is, do you need, for example, tri-diagonal sparsity so that you have one main diagonal and some subdiagonals, or is it arbitrary so that you can have sparsity somehow, like when you think of a matrix vector multiplication, that you have some sparse points but no real pattern?
Yes, so the sparsity can be any type. Then QSS will help. Doesn't need to be on the diagonal or the...
Okay. And sorry, last question is, do you want to integrate your functionality in the SIML ecosystem?
Yes, although the internals or the QSS method is a lot different from the classic methods. So they have the step function and the init functions. I cannot go and use those, but we can integrate it in a way that they will have my problem and my solver or my integrators, and then they can have a wrapper around them and use them and integrate them in the CML. But I cannot, because I looked at the website, and if I want to extend the CML using QSS, I had to adhere to their some of the functions. I had to use the init and step, but if it's not possible to use them with QSS. So I guess if they can have a wrapper, since we have the same interface, so I'm not sure.
All right, let's thank the speaker again. Just a short announcement. So we'll have a short 10 minutes break, and the keynote starts at 5:10 instead of 5:30. So please go to the main stage at 5:10. Thank you.